Do you have the pointer by any chance, like the device to change the slides?
Research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and bright minds. A community united by the power of science.
The first one. No, go because there are many. The very first one. I think it's faster if you wax it because.
Looking for something, some search for a treasure, some for inspiration. Looking for that which will be found in our museum. Multimedia, the only one of its kind globally. Visit the main campus and through the telecommunication journey. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to our Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they face. Here, everyone speaks one common language, science. Basic and applied research are both vital for society, from fundamental particles to black holes, quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. Encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity,
Morning.
and promote bright minds.
Good morning.
The community united
We'll start
by the
today's
power of
section. We have again Alessia Candeo from the Polytechnic Institute of Milano, and she will continue with imaging techniques. The floor is yours.
Thank you very much. Good morning. I hope you're all good. So here today, I will go on with my talk that I started. Okay, we talked. I've shown you the system over there, but then I also talked about microscopy, and we put emphasis myself, Professor Silvania Pereira, on the resolution. So good. So I was a lot of emphasis on resolution, on the capability of visualizing. We said, okay, there is the limit in the airy disk. We cannot see something that is smaller than the resolution. Where is that? Today I will start by talking about the capability of going the resolution limit, things that are smaller than that. I'm not an expert, so you probably will ask questions that I don't know, that I don't know. Okay, so I might not know the answer. But, you can still ask me. It's not my field of expertise, and if I don't know the answer, we can discuss, try to find the answer to it else. So, but let's start with this. Okay, we can in fact go beyond the limit. Going beyond the resolution limits means that even though something might be wide field microscopy or with other techniques blurred, like for example in this case we're looking at the nucleus of a cell. In fact, the nucleus is made of units smaller than what we can actually observe. So the idea is we would like to be able to see things that are smaller, than to have a higher what we are looking at. Okay, is that possible? There are two main approaches. The first one is the deterministic one, like the one that we are used to. You illuminate something, you look at it from yourself. There are other based on statistics, okay? So while the deterministic approach position, and that's it, in the case of the stochastic approach, you don't really look at the thing, but you look at the probability of finding a molecule in a specific position. Now I will try to expand on this subject. I will start with structured electroscopy. Structured electroscopy need the use of special probes, fluorescence microscopy, actin fibers from a cell, and on the left side here we have the wide field image. Okay, this is what we can see without breaking the resolution limit. But actually, we would like to be able to see finer details that are actually present in our sample. Okay? If we think about what it means, we have finer details that we can see very abrupt changes, for example, in the contrast of your image. Finer details, so higher resolution in your image, means having an higher frequency content in your image. It means that you can see frequencies that are higher, because these are frequencies that are lower, they are more. Okay. Finer details, higher resolution, means our frequency content. So I'm starting to talk about the frequency content, meaning that we can look at the resolution with its reverse. The verb in its so the maximum frequency that can be resolved is 1 over the Airy unit, okay, the Airy disk, 1 over D, Airy disk. So K is the maximum frequency. And as Professor Pereira told you last week, we can go from the spatial domain to the frequency domain and talk about optical transfer functions. So the optical transfer function is this kind of drawing, this kind of graph, where we have the maximum frequency that our observer Z direction. Well, here it says Z, but actually it should have been X. In the Y and X direction. This circle tells you the maximum frequency that you can observe in your sample, and what your system can detect are all the frequencies that are included in this circle. The optical transfer function of a general system depends on the detection capabilities of it. Okay? So your image in your sample might have frequencies that are present, many small molecules, but maybe they fall outside of your OTF, of your optical transfer function. So that is outside, you are not able to see it because it's beyond your resolution limit. Okay, how does structured illumination works? In structured illumination, you overlay your image, your sample, with a pattern. The simplest probably a sinusoidal pattern, like the one that I'm showing here. And if you imagine you have you observe is a Moiré pattern. So you observe another pattern that has a periodicity that is twice. Okay, sorry, which has a periodicity that is half. So a frequency that is, oh God, I'm messing it up. I mean that you see a pattern with a frequency that is lower than the initial one. Okay, so it's easier to observe this initial one. Not too obvious what it means, but let's go to the frequency domain and try to understand what happens when you overlay your image, which has a specific frequency pattern, which has a specific frequency content. So this one is now again the OTF of your image, and it is just linked to your detection system. So the green part, the green circle is what you can observe anything else. The yellow stuff, you cannot observe it. So now let's our pattern frequency domain. Sinusoidal pattern, it's easy. In the frequency domain, it's just these 3 dots, okay? Because you only have the turn. Are 2 outer dots of your superimposed pattern, okay? That you obtain these 2 circles. They are 2 replicas of your initial. You can only observe what is inside this circle, okay? You cannot on just this replica on the upper right. You have some of these frequencies that initially were outside of your OTF, that now end up inside your OTF, okay? And these frequencies are frequencies that are higher than the ones that you were able to detect in first place. But now you can, because you multiplied them by your pattern. And of course, the same goes for this other replica. You basically manage to, oh God, okay, the colors have changed. This ended up inside your OTF. So some of to be observed now by your OTF. Not all of them yet, but then if you take your pattern, you rotate it many times, you get this nice. By rotating 3 times your pattern, you manage to bring many, all of the frequencies that are here around your OTF side of it, your OTF, and so now you can observe them. So in this way, you can increase your resolution of 2 times. 10 times, 2 times, which is already good. You have improved of 2 times. And of course, because the sinusoidal, you also have to translate it. Otherwise, there will be some parts that will be dark. So for example, I don't know if it's visible, but this is a cell with a superimposed pattern, a sinusoidal one, and shifting the pattern quickly. And you see that sometimes some dots are illuminated, sometimes they are not. So we need to rotate to cover the overall, to cover all the to illuminate the field of view. So, of course, we need to acquire many images, 3 rotations and 3 translations. So it's not it's with wide field that you acquire just one image, but here you increase the resolution. How do we do that? How do we create the image? I will on the conventional method. So to create a pattern in like that, do is we access the OTF, the frequency domain. And you might have understood from that, for example, for an objective, the pupil plane, that's a Fourier plane for the objective. Okay. So what we do is the following. We take one beam, we create 2 replicas of that beam, for example, with a grating. Okay? A grating like the one that Professor Pereira showed you. And we send the beam. The objective, and the objective sends them collimated with an angle at the focal plane where they intersect and they create an interference pattern. You can create an interference pattern in this way, that is sinusoidal, that will be superimposed with what is present at your focal plane. We can acquire many images in order to obtain finally the super resolute one. The only way are also other types of patterns that allow you to reduce the number of images. Today's talk. Of course, this means that we have to take all these images, and we need to put them all together somehow. So there is quite a difficult, opinion, reconstruction algorithm that must be run to put together all the components in order to retrieve the image. So this method implements many images, them, and you can observe your super resolved image. Okay? So this is an example. You can see that the wide field image looks a little bit blurred. Improve the resolution, the structured illumination. So we can see finer details compared to the initial ones. I will now move to another method, which is still a deterministic technique, and it's called stimulated emission depletion microscopy, or SED. This method, together with the next one that I'm going to show you, got the Nobel Prize 2014, because super resolution was awarded a Nobel Prize, but interestingly, it was awarded the Nobel Prize in chemistry, okay, not in physics. It was in 2014. This stuff was so useful for chemistry because finally that you couldn't before, that they gave the Nobel Prize to these techniques, improving our knowledge of chemistry. So how does this STED works? So it's you have to start to think with about STED like in confocal microscopy. But here we don't have the pinhole. We have something else that will create the super resolution effect. Okay, we have our excitation beam, and you have to imagine here that we have some molecules. To think of our fluorescence from the sample as made of many molecules that are being excited, and they emit sunlight. So with our excitation beam, we illuminate a certain area, and the spot, the illumination spot, is limited by the diffraction limit. Okay, now the trick here, because it's a trick, all of these are tricks. Nobody is actually going beyond the resolution limit, but there is a trick. Basically, the STED laser beam. So this STED laser beam is a second beam, very powerful. Both these beams are actually pulsed laser beams. The STED laser beam is shifted at longer wavelengths, and it is longer in pulse duration. And this laser beam is sent to the sample right after the excitation laser beam. This beam is strong that when it hits the molecules, it creates a stimulated emission from the molecules, and they are depleted. So they enter into a dark state. So they are not emissive anymore. This beam is sent through a phase plate that creates a donut. So we talk a lot about donut-shaped beams when we talk about STED. So red donut, this red circle, annular circle with an empty spot in the center, is a beam that will deplete all the molecules on the outer part of our illumination beam. And only in the center, we will see fluorescence. Okay? If we increase the power, what is going to happen is the central spot will become smaller and smaller, and eventually, with the higher and higher laser power, we can illuminate single emitters. Thanks to the fact that we can illuminate, like with a very tiny pencil, only single molecules, we can improve in the resolution, in the perceived resolution that we have in the final image, right? With this technique, I don't remember, I think in the first paper, they were talking about a resolution of 60 nanometers. Now they go to 20 nanometers. 20 nanometers, 10 times better than standard microscopy. Of course, in this case, I've shown you resolution on the illumination beam. The higher the energy, the higher the intensity of the STED laser, the better the resolution. Sometimes this can be a little bit dangerous, of course, because if you have a dead sample, the higher the chances of burning the sample. Okay? So for this type of technique, I have to say that you cannot use standard fluorophores. In fact, there was a lot of search for new probes for STED that are more photostable, that they don't bleach that easily, that they are efficient in this simulated emission due to the presence of the STED laser beam. There was a lot of work developing new probes for STED because it was recognized as important to find new probes. So there was a big push in chemistry as well. And I can also show you what happens to the PSF again. So if we add the donut-shaped beam, and we increase the power with 10 times and so on, we can reduce the PSF, okay? So we can improving the resolution limit. So I think this was the first schematic that was presented, and this was the first STED image that was shown by Stefan Hell. Okay, so you can see here that in this wide field image, you cannot see single filaments, but when you activate the STED beam, you increase in your resolution and you can observe single strings here, single fibers. Types of samples, work on the, as I said, there has been a lot of work also to try to reduce the power that is needed to have the stimulated emission in order to make STED more gentle as a technique. Here we are looking, for example, at mitochondria. Before, in this case, this is confocal and this is STED. So you can see that there is an improvement in the resolution. Here, even the cytoskeleton of neurons before and after STED. And you can see here that you can observe fine structures that here were completely not observable. And in this technique, differently from structured illumination, you don't have to reconstruct. Okay, so this is a direct, it's more direct as a technique. The problem is that it's tricky. It's very tricky. It's not easy. You have to find the right conditions, but it gives great results. And it was possible to even observe the membrane, basically these are the nuclear pores. Here, this is the confocal image, and this is the comparison with the STED one. So you can really see, it's almost, they have nothing to do with each other, these two images, but you can observe the nuclear pores, the constituent of the nuclear pores in the nuclei of cells. All right, I will just give you the last one, the last method. This is a different one. This is a stochastic method. All right. So this is called single molecule localization microscopy. So in this case, this is, as I said, it's a stochastic method. So the question I might ask you is, okay, I have a single emitter. I have one molecule. I show you this image and I ask you, where is the molecule? Can you hear me? Yes, okay. So if I show you this image and I tell you there is just one molecule in this image, can you pinpoint at it? Can you say where the molecule is? I don't want to see the molecule. I don't care about seeing the molecule. I just want to say where the molecule is. All right? Well, I think I can. Well, honestly, if you ask me, I think the molecule is here. Why should it be here, for example? There is no reason. The molecule is there. Why? Well, that's where you have the highest energy, the highest intensity. Why should it be anywhere else? It's there, I cannot see it, but I can say it's there with the highest probability. I'm not 100% sure, but the highest chances that the molecules are here, yeah, well, that's something I can say that is there. That's the point of highest chance of finding the molecule. Okay? I can just, you know what? Why do I have to keep that image? I know the molecule is there. Why I don't just doesn't like the, okay, yes, that's what it is. Create an image made of the point that I say, okay, the molecule is there, and I create an image, my perception, where the molecule, of my localization of the molecule, instead of the image of the molecule. Okay, so what does it mean? It means that if I collect images of single molecules that are not super resolved, I can still fit the distribution of intensity that I observe and pinpoint where the molecule is with the highest probability. So this is stochastic. Okay. In this case, we move from the concept of resolution to the concept of precision. I have to be as precise as possible in localizing the molecule, in being able to say where the molecule is. And of course, the precision increases with the number of samples I collect, with the number of images, with the signal-to-noise ratio. Okay? The better the image, the best signal-to-noise ratio I have, the more images I acquire, the better my localization capability becomes. If I collect many samples, I have more chances, I have a better statistic. I have more chances to precisely detect my molecule. How can I? Oh, thank you very much. Thank you. So the precision of localization can increase if we have molecules, for example, that shine many times, that they blend. Okay? Let's see if this is okay. No, I'm going back. Aha, sorry. Okay, so if we collect many samples, because our molecule may be so it turns on and off many times, what happens is that we in our capability of actually being able to say, okay, sensitive detectors, like for example, usually for this technique, we use EMCCD cameras. They are not as fast as CMOS cameras, for example, but they have a high quantum efficiency and they have a small readout noise. So this helps in collecting better signals and with higher signal-to-noise ratios. But there is still a problem, because if I have two fluorophores that are still too close, one to each other, I still will have uncertainty when it comes on, to say where the two molecules are. If I don't know how many molecules I have in one spot, it's difficult for me to say, oh, the molecule is here, the molecule is there. I need to know some a priori knowledge of the number of fluorophores that I have in a specific point. So if I have two molecules that are too close, this is not going to work. But if I have a sparse collection of molecules, then this gets better. And how can I have a sparse population of molecules? Well, either I have few fluorophores, but maybe I don't, that's not what I want. And so what they, again, used, it's blinking fluorophores. I already mentioned that improves on your capability of acquiring many images, but also on the fact that if you have fluorophores that turn on and then turn off, and if you can manipulate the timing of these fluorophores, the probability that you will have two fluorophores that are very close to each other, that are blinking at the same time, is very small. Okay? So if they blink at different rates, so when one is on, the other one is off, for example, it's easier. Is there, and the one just next is there, because they are active at different times. So if the fluorophores are sparse or they're blinking, okay, this is going to work then. And in fact, also in this case, there was development of new types of probes, to switchable or activatable fluorophores that blink, basically, okay? And this, so basically, these are fluorophores that, after a while, they switch off, they go into a dark state, they bleach, but then they can turn on again. They can blink again. There are different types of these fluorophores, and this technique is called PALM. It's photoactivatable localization microscopy. There is also STORM that is different, but not too different. It is based on a similar concept. And also this technique got the Nobel Prize in 2014. The common image that is being shown of the Eiffel Tower every hour. I don't love this image because, anyway, I don't think that is very in but I will still show you. So this is your original, okay? And the Eiffel Tower, it blinks, detect only the blinking like that, and you put them all together. At the end, you can reconstruct from the blinking the image of the Eiffel Tower with a better resolution compared to what you beginning. Okay? So the idea is you have many blinking points. For all the blinking events, you say, okay, the molecule is there, and then you put all the blinking events. Okay. This is what you see when you have a molecular, a biological sample. This is a cell. You illuminate your sample. The molecules blink, like very fast. You average the data, you get your wide field image. So that's what you would see if you were looking at the same sample with a wide field image. And the last one is the PALM. So it's the reconstruction of the localized events. And in that case, you can see those dots. They are indicative of the presence of single molecules. So the resolution that you can obtain there is, again, in the order of tens of nanometers. And it was possible, in fact, so this is it, you see, in a small region, like in this region here, this is what you observe with white. But actually, that you see the single, okay? So, okay. Oh yeah, that's turf. It's not standard microscopy, but it's fine. Okay, let's go back. It's too late. It's gone. It doesn't matter. But what I wanted to show you is what you can get. So for example, you have this fixed cell with microtubules that are marked. This is the white field. If you focus your attention part of the two strands of microtubules, but in fact you have four. Okay, so very fine structure and even quantify single molecules. Okay. Any questions about this? Any curiosity or anything we can discuss as well? So this part is very, this part that I just showed you, the part on super resolution, I believe is something that is, I wanted to show you because if you look up microscopy right now, in the last years, it has been all about super resolution, of course. Most of the developments were in super resolution. So if you want to learn something new, and you look at the last important papers, they are all about techniques that are like these ones. Okay. But now I would like to go on in our journey in microscopy and talk about again something I've already introduced the last time, which is contrast. We talked about contrast when I mentioned that we can, have contrast even with by adding dyes at your sample and still looking at your dye in transmitted mode. You can have contrast if you add fluorescent markers. And now I want to talk about the other two ways of adding contrast to your image. Okay. Okay, perfect. So to do that, I'd like for a so I think I should have done all these talks in reverse, but it's not a big deal. Who knows what it is, a Jablonski diagram? Of you students know what it has ever seen a Jablonski diagram? Maybe I'm not pronouncing it well, but I want at least one hand up. Who has seen this graph before? It is the graph that shows us the structure. It's just a graph, let's say, a schematic of the electronic and vibrational states of a molecule. Okay, usually we say, okay, so you are lying because nobody is saying I've seen this, you are lying because I have shown one last week, so I should have said that I've seen a graph like this. But now I will go a little bit more in the details of this. So, okay, when we look at this is a schematic of a general molecule that has a ground state here, two excited states, and a triplet state over there. Okay. And when we excite a molecule, for example with photons, we basically determine the absorption of photons that bring your molecule to the excited state. Excited state, then femtoseconds, 10 to the minus 15 seconds, and then you can also go on and bring your molecule to an excited state, okay, again in femtoseconds time scale, 15. Then you can have some vibrational disexcitation inside the excited state in the time frame of 10 to the minus 15 seconds. Internal conversion, second state to the first excited state, that takes place in 10 to the minus seconds. And you can also have emission of fluorescence. Fluorescence takes place in nanoseconds. Okay? Fluorescence takes place in nanoseconds. And basically, it's the recombination of the first excited state to the ground state through the with the not the only way. Okay. We can have the disexcitation of the molecule. We can also have, for example, intersystem crossing from the excited state to a triplet state. And then from the triplet state, we can have phosphorescence emission. Phosphorescence is similar to fluorescence, but it happens in a time scale that is longer. It can take microseconds, milliseconds, even seconds to take place. Okay? And in fact, these two are not the two only ways that we can have the excitation of the molecules. These are just the radiative. Because then our molecules, they can de-excite even with, because of thermal effects, the mechanical stress. There are many ways the fluorophore to the ground state, non-radiative. But the radiative pathways are mostly these ones. Okay, I want to show you this because I mentioned the fact that when we talk about spectra, excitation and emission spectra from a molecule, somehow the distribution of our excited states, okay? We are somehow studying how our molecule is built. What is the electronic of our molecule, okay? So we can have the excitation spectra or absorption spectra that shows the energy distribution of the absorbed light, okay? And basically tells you something about the from state to the first and second excited state, or all the excited states you might have. And emission spectra that tells you something about the energy distribution of the emitted light corresponds to this excitation of your molecule from the excited state to the ground state. Okay, so if you study the spectra of your molecule, of course, you are studying the properties of the molecule itself, how its energy levels are distributed. This is also directly linked to the Frank-Condon principle and blah, blah, blah. I'm sure you know this better than me. But I think it's important. There are other two things I want to recall. One is the quantum yield. What's the quantum yield of a process? It is the efficiency of the emission of photons from a molecule. So basically, it's the number of emitted photons by the number of absorbed photons. And of course, this has always to be lower than 1. Okay? Yield tells how efficient your molecule is in giving back photons after absorbing them. And I want to stress there is the emission, so there are radiative phenomena, but then there are also non-radiative phenomena. Non-radiative phenomena are the molecule is bumping on the table. And if it bumps on the table, it transfers energy. Or it can interact with other molecules and transfer energy. And so it loses energy. Hence, there are non-radiative ways of this excitation of our molecule. So the quantum yield is also defined as the rate of the radiative decay process divided by the sum of all this excitation rate, those that are radiative and non-radiative. Okay. Now there is a last quantity that I want to discuss, because this is a really interesting parameter. I really like this parameter, which is the emission lifetime. Okay, so what's the emission? It is that a molecule spends in one excited state. So I said, okay, it takes a little the molecule to go back to the ground state. Okay, so we have all our electrons, we excite them to the excited state. We have a large population of electrons in the excited state, but then they start to fall down to the ground state. The initial probability of this electron to reach the ground state is higher compared to those that are left there, because you have more of them, okay? So at the beginning, many electrons that go back to the ground state. And then with time, all of them will go back to the ground state. The time constant is characteristic of the molecule. The time it takes to a molecule ground state is all of that. Okay? processes like fluorescence and phosphorescence, they take place following a first-order kinetic, which basically means, I don't have the laser anymore, which basically means that the population of the excited state follows a dynamic that is exponential. And this exponential is exponential to the minus t divided by tau. And tau is the lifetime of that excited state. Tau is the constant of the decay, and is defined at 1 over plus rate of non-radiative disexcitation. So it's 1 divided by the sum of all the rate of disexcitation. So not only the radiative one. Because it is a property of the excited, all right? So how can we explore the decay time? We can, for example, send a pulse, a flash of light, to our molecule, like for example here, a short flash, like when you take a picture, okay? And this flash will bring your molecule to the excited state, and then we can look with a detector at the photons that are emitted, at the emission, and we can explore how the intensity changes along time following this exponential rule, and we can retrieve tau, okay? The lifetime, it's dependent though also on, for example, non-radiative processes. And in particular, it is an interesting parameter because it's sensitive to the quantity of light that you send to your sample, because it's characteristic. Once your decay and you feed with an exponential curve or a sum of many exponentials if it's a non-exponential decay, you extract tau, which is independent on the intensity of the illumination that you're sending. So if, for example, you have a laser that is changing in intensity over time, you have a more reliable parameter compared to monitoring the intensity of emission. You have the lifetime. It is characteristic of the excited state. And also, it is a parameter that is sensitive to the microenvironment of the molecule, because we said if the molecule bumps on other molecules, well, there is this excitation. And we can monitor that. So we can monitor the characteristics of molecules inside the space. If there are changes in the environment, we can monitor through the lifetime. Okay. How do we do that? So one way is to send a train of pulses, let's say many pulses, one after the other, with a pulsed laser. And then I am making it very simple, but the concept is the following. And then you detect the photons that are being emitted by your sample, and you have a stopwatch. You assign to each of the photons that you are collecting a score depending on the arrival time, the delay with respect to the excitation pulse. Time, you have another one that arrives after a certain time, and you have another one that arrives at time. Sometimes you don't detect photons, but the idea is that you have to consider the arrival time of your photon with respect to the excitation pulse. And this is a photon counting system. You have to count the number of photons, and by doing so, by creating then an histogram of the photons that you have counted with respect to their arrival time, so an histogram of photons versus arrival time, you can reconstruct, create electrons, more electrons in the excited then with time you have less and less and less, the probability becomes smaller. So you have your decay through this histogram. Okay, this is an example that you might have seen in the past, maybe, I don't know. This is an example of time-correlated single photon counting curves that you can collect with a system similar to that one. Of course, there is a lot of electronics involved. The idea is that you can collect photons as a function of the arrival time with respect to a pulsed laser that excites your molecule. Usually, we show curves in a logarithmic diagram, in a logarithmic plot. You see a straight line. Decay. In this, for example, we had fluorophores that were embedded on a substrate, let's say. Sorry, this is not actually my experiment, but anyway, what happened here is that they measured the decay, and they got this grid curve, okay? They can retrieve the light, which would be probably dependent only on the radiative decay constant. And then what they do, they put these in solution, and all these fluorophores, they go in the solution, and because they're more free to move, they interact with the environment. There are no radiative pathways that are opened. And it happens because no radiative pathways that are being opened, the molecule is excited faster, and indeed you have a faster decay curve. Okay, because this curve has a slope that is to the first one. 10 minutes. Okay, that's fine. Okay, so what can we do with this? Well, we can do this coupled with a confocal system. We can record these lifetimes for every pixel, for every point, let's say, in our image, and we can create maps of lifetime. Okay? So this is an example that I took from a company. You move from an intensity-based image, like the left, where you don't have contrast, because everything looks flat, same color, to something much more colorful. You have contrast here. This is just an image of an Arabic Italiana root. And you can see that you can discriminate the presence of actin fibers, other image. And that image is so computed. They computed the lifetime, and they assigned different colors to different lifetimes. For example, in this case, you can also extract the lifetimes themselves. Here you might notice that the slope is just slightly different, but that accounts for a big behavior of molecules that are present in that cell. In this case, we are looking at a FRET, forced resonant energy transfer effect. So in this case here, we have molecules that interact less, and indeed the lifetime is longer, because you see that the slope less pronounced. And where the color is yellow or more red, you have high forced resonant energy transfer, high non-radiative, high transfer of energy between one molecule to the other, and this makes lifetime reduced. And so you have a slope over there that is higher. We can do this with the time-correlated counting, but there are also other techniques to perform time-resolved experiments. I think I'm going to skip this, and I will just give you a glimpse of the very last subject I want to touch. I'm not going into the details because, but I will basically just conclude with a picture of myself. So that's not just a standard picture, though. That's a picture that is more than a photograph. We have, you see it, but actually each pixel in this image contains another information. It's not the lifetime decay in this case, but it's the spectral one. So if it is an image that was acquired with an hyperspectral camera. So in this case, I want to just mention that, of course, we can reconstruct the lifetime to study our molecules, but we can also study the molecules that are present in the field of view, spectral properties. Okay? There are different ways of doing so. If we think about spectroscopy, the easiest way of thinking of the study of is basically just a piece of glass, it's like a prism, and put it in front of a ray of light and see the dispersion into all the different colors, so the spectrum of the ray of light that we are considering. And of course, if in front of our prism we have a line detector, like an array of detectors, we can record the spectrum, that, the spectrum of the light that is being observed, and we can infer what are the wavelengths that are present in that ray of light. The problem is that we want to collect this information for an image, not just for a line. Okay, so there are many different ways, and the easiest way of being able to record an image with those spectral information is through snapshot imaging. Some cameras where the pixels actually are not single pixels, but there is like a colored matrix in front of it, and actually all the collect many different colored pixels. But these cameras are not very efficient because the spatial resolution is not very good, because you are wasting many pixels, and the spectral resolution is not good either. Another method that is probably the easiest one and the most cost-effective one is the staring imaging. Basically, you acquire many images of your field of view just by putting in front of your detector filters, and then you acquire many images. And then there is the so-called push broom imaging technique, where you have a spectrometer that basically separates your, or a prism if you want. Oh, sorry, yeah, I meant a dispersive element like a prism or a grating that basically disperses all the wavelengths spatially. And then you have a line detector that you move so that you can collect many of these spectra per line and then reconstruct an image. This approach has a very high resolution from the point of view of the spectral resolution, but it's very slow, okay? Because you have to collect spectra, one spectrum per line. One spectrum per line, then you have to move. And it's also not the most stable way of going on, of acquiring this type of image. There is another couple of, I'll give you one image and I go. Basically another way of performing spectral imaging is a method on Fourier transform spectroscopy. So the Fourier. In this case, what we do is we have a ray of light and we create two replicas somehow. and the two replicas are delayed in time. What you can do is you can change the delay in time and let the interact with one each other. And in this way, you obtain, if you record with the detector the effect, you obtain an interferogram because you are making the two replicas interfere in time. And if you obtain the interferogram, from the interferogram, you can then reconstruct through Fourier transform approach a spectrum. Of course, this works in 1D, but we can use in point detector a camera and acquire many 2D images that is interferogram, a so-called hyperspectral image. This is the hyperspectral image. Hyperspectral because we can reconstruct a continuous spectrum. The simplest way of creating interferogram is using a Michelson that I think most of you have seen and maybe also used practically. With Michelson interferometers, you can create the two replicas with a beam splitter, and you send the two replicas to two mirrors. And by moving one mirror with respect to each other, you can tune the delay between the two replicas, and you can record the interferogram with the camera and then transform it in a spectrum and obtain the temporal a spectral hypercube from the temporal hypercube. The Michelson interferometer is not the most, let's say, stable interferometer because it's actually commonly also to measure vibrations or gravitational waves. Okay, so it's very sensitive to vibrations. So there is another method that we have developed that is based on crystal and refulgent crystal. You know what? I don't think this is useful. That I'm going if I show you this one. So I'm just going to go through it and I give you an example so that I don't take too much time from the others. But I can discuss this another time. Let me just quickly go to one experiment. So this is just to give you an idea of what we can do with these hyperspectral cameras. It's the following. In this case, we had some I work a lot with conservation scientists. I have the luck of working in the cultural heritage field as well, not only in biology. And in conservation science, now there is a big discussion on, let's say, the study of biofilms on stone samples. The idea is that we want to understand how biofilms grow on different stones, to understand if it is worth removing this biofilm, if it is not worth it, and does the biofilm grows in first place? Is there a way to reduce the growth of this biofilm? You have to imagine that we have that in Italy we have statues that are in open air. We want biofilms green. We want them to be very nice and with this, basically, you can select different areas in your sample and you extract spectra. Okay, those are reflectance spectra. You can extract from the reflectance spectra of the reflectance. Okay, and you can create false colors image, okay, that are dependent on the wavelength of the peak of the first derivative, that is correspond to the flexum of the reflectance, and you can create false colors map that allows you to enhance differences that are present in your sample. And you can also not only do reflectance, you can also perform fluorescence studies. So in this case, we are exciting the fluorescence from our sample. We are collecting the hyperspectral image of the emitted fluorescence. We can create false colors image. In this case, the image is showing us that there are two biological states present on our stone sample, even in areas where we didn't think that there was a biofilm that was present. We can, again, extract the fluorescence from different areas, and we can study the fluorescence spectrum in different points spatially. Very interesting, because we understood that there are because we can access basically to the fluorescence of two photosystems that are present in the biofilm that tell us that there are some portions of our sample that are under of our sample really bioactive. And other areas that are instead dying. Because we can see, for example, the shift in the main peak of the or between the two peaks. So I think that I'm going to stop here because I don't want to take more time from the other speakers. But we can discuss this further if you like in the next few days. So thank you very much for your attention.
Thank you, the speaker, for the nice presentation. We have a little delay. Please, very short question. You can take 1 to 2 questions.
Okay, I think we can.
Question. Let's thank the speaker again. Alessia will be around, always available.
I'm always here.
Okay, and I will present our next speaker from Multimedia University of Kenya. Is Dr. Elijah Ogaro, and he will present laser spectroscopy of atomic system. Thank Dr. Ogaro. The floor is yours.
Yeah, good morning. Yeah, it's another time that now we have to look at laser spectroscopy. At this time, we shall be resolving energy levels and not the images. So let us switch gear and discuss about what we do best in laser spectroscopy. And our sample is the atomic vapor. And the atomic vapor is at room temperature, so that is what we shall have to look at. And for the sake of students who are here, and therefore to capture the audience so that I keep him as much as possible, staffs, and his staff, mature guys, doing research, the master student, PhD students, and then the higher levels also. Therefore, let us start. I will do the introduction. Then we do some stuff on measurement of the hyperfine levels of rubidium-87. Then we shall do some resolving technique of trying to resolve some energy levels through Rubidium-85 as some of the energy levels which are, and therefore attempt to resolve them. Then we later look at the application of part of what we have used in resolving levels. Where can we apply it? And lastly, I will take you through what we are doing at NIHOL, what kind of research, because that is what we shall have to look at and see. So, let us begin. What is the reason of us doing measurements? And that is basically what we are trying to highlight. Atomic spectroscopy. Why should we do atomic spectroscopy? What are the benefits? One of the benefits is to stepwise the laser at a particular transition. And this is very essential, especially when one wants to do some experiments. For example, laser cooling experiment, that is laser cooling and trapping. This is very important because you want to stepwise the laser at a particular that you can with a particular, and then you can laser cool them. There is also another benefit of coherent manipulation of atomic states. This is very important, especially for quantum computation. And for example, in this transition here, 5s to 6p to the red. Initially, this is the proof transition. It's using IR transition. It's been done. Is that the this is the brute transition, and then there is an IR transition to the red back states. What has actually been done to trace the IR transition, that is a 5B state, and then you can move to the red back state. And therefore, because most of the research has not been done in this area, and therefore it's very important for us to concentrate on the proof transition such that we create more data in this area. The other reason spectroscopy is for precision measurements. We want to know, for example, what is the absolute frequency for a given transition. This is very key. And also, especially for applications such as atomic clocks. For example, if you look at your watch, either the watch of your computer, your phone, if it doesn't lose time, wherever you are, but the manual clocks loses time. What is the essence of that? It's because of this precision measurement, which is synchronized with the internet, so that your watch or your computer will set the time as long as you are on the internet at any given moment. The of, for example, hyperfine measurements are important to extract these hyperfine constants, which gives us information about the atom. That is, magnetic fields and the nuclear magnetic fields, that interaction, they can best be extracted from that kind of information. Now, let's look at what happens when a laser interacts with an atomic medium, and this is for a two-level system. This atomic system, when it interacts with the laser causes transition. That is, if we have an atom at the ground state, then this atom will absorb the energy of that photon, and then it can move to the excited state if the frequency of the laser matches this difference here between two states, and that when we have the absorption. So the blue curve here gives us the absorption of that. We can always calculate this, and we apply the Schrödinger equation, which gives us the various dynamics on how the atom interacts with the laser. Now, in this Schrödinger equation, we have various terms here. We have the Hamiltonian, And this Hamiltonian is the energy Hamiltonian, because when you are shining some light on, that is the laser on the atom, then giving the atom some energy, perturbing that atom. So this energy Hamiltonian possesses the energy that you are giving to this atom. And therefore, we can then, of course, we have the wave function. This wave function is what contains all the information about the atom. I'll try all evaluate for that case. And then we have the generalized equation, which we call the mass equation. And from here, this is the density matrix formalism. And matrix formalism, then we have the coherent term of that density matrix. And this coherent term here is always proportional to the absorption of the probe or the laser for that case. We can always evaluate element-wise what is the contribution of what is contributing to this curve here. And that, for example, for the two-level system is nothing but the difference in terms of the population between the ground state and excited. That is what is bringing about that difference. And for a two-level system, the ground state population is always higher than this excited state. And as a result of that, then you have that green curve, the blue curve. Another thing that happens, the refractive index of the medium also changes with the frequency. As you are detuning your laser around this excited state, and the refractive index also changes. And absorption is maximum when the refractive index is actually 0. And that is what we can be able to see that. This is also known as the dispersion curve. Now, away from that, there is also another effect that happens when you shine some light on the laser interacting with an atom. It does not only cause transition, that is the movement of the atom from the ground state to the excited state, but it also the energy levels of that atom, because the laser is an electromagnetic field, so it has the electric field. And as a result of that, the energy levels are shifted. This idea of shifting the energy levels when you are, depending on the tuning of the laser, with respect to this transition here, then because you are using light to change or to perturb these energy levels, then this is also known as light shift. This is because of the Stark effect. And if the laser, for example, is detuned below resonance, then this will cause this transition here, that is the excited state, to shift upward. And then the ground state will also shift downward. This, in essence, causes what we call the change in the transition frequency. The transition frequency was here, that is, we have the dashed line here. And then now the original energy levels are not in that position. They have changed. And that is what is causing this shift of the transition frequency. So this is for the laser that is red detuned. In other words, it's detuned below resonance. So cause a different kind of light shift. Transition frequency reduces. In the first case, it is increasing, but in this case here, it is reducing. If you have that is, the detuning of the laser is 0 resonance, then you will split these energy levels. In this case, so you have energy levels being split and shifted away. And in essence, then, this has an effect. Sometimes we want to evaluate this effect here. But for a two-level system, it's usually not possible for you to evaluate what is happening in this case here. For example, what has happened here. Because of in of the effect, his saturation effect. You have a weak probe, try to evaluate what has happened here, then sets in, and as a result of that, then you don't be able to see this effect in essence. There is also another effect that sets in, what we call the pitting, or is also known as coherent population oscillations. Two lasers that have the same polarization, and these are counter-propagating, then they will start to interfere. And as a result of that, then you have what we call coherent population oscillations. So these two effects, in essence, inhibits you from seeing what this strong pump has done for these two levels. And therefore, to see that effect, we need another level. In other words, we require a third level. And that is, now we have moved from the two-level system to a three-level system. For this three-level system, we can have our strong pump hitting this transition here, and then we can now check and monitor exactly what is happening with a weak probe that is now coupling the same excited state, but from a different ground state, that is on a different transition, but they share a common level here. This kind of a system is known as the lambda system, just from the shape of this figure here. Now, so the splitting here are what we call the dressed states. These are the new states. They are not the original states when we did not have the laser in place, and therefore they are what the pump has done as dressed the system. It has created new states. And if you scan your probe across the dressed state here, the probe experiences absorption when it comes to the first state, but right at the center here, it will experience a drop in terms of absorption because the energy levels have been split and shifted away. So there is no energy level at this point here. And that is what exactly we see here. But this is also enhanced because of, if you look at this figure here, this excited state and this dressed state here, the two dressed states, they are coupled or connected to the same excited state. In essence, then, we are talking of the same excited state. So if you excite an atom from this ground state, then it will go to this excited state. But there are two routes. Either it goes through the first dressed state or through the second dressed state. And eventually, we are talking of the same excited state. That creates uncertainty because there are two excitation pathways that is to the same excited state. And as a result, that leads to interference. So this is what is known as quantum interference because of these two excitation pathways. And hence, the deep here is actually enhanced, and it can go down to the zero as a result of quantum interference. So there are two things here. One, the energy levels has been shifted, split and shifted away. And therefore, if you tune your laser at the right center here, you don't see an absorption. And that is further because of quantum. We study this one. The system now starts with this ground state here, 1. And then we try to measure or determine or calculate the rate of change of population from this ground state here. That is 1. And since we know that our probe is very weak, and therefore, in that weak probe regime, population transfer is usually negligible. And as a result of that, then we can try to calculate what is the rate of change of population. That can be calculated from this part here. This is the rate of change of population. But this probability amplitude can be further split, and we have that part. So if you can be able to calculate the change of this probability amplitude, which is the same as this, because this is the complex conjugate of this one here, then, in essence, that is what is represented here. So we have the light shift as a result of the two dressed states that have been created here. So we have the first dressed state, we have the second dressed state, and then we have the interference, that is the quantum interference term here. And therefore, in this equation here, you have all that contributes. I think that is enough for the motivation. So let us switch gear and discuss about measurement. And in this case, we are going to use double resonance. And in double resonance, we shall try as much as possible to measure the hyperfine interval of rubidium-87, 6p a half. What is the hyperfine interval here? So in this case, double resonance, as the name suggests, it is called double resonance of the fact that this laser here, which is the probe, is coupling a strong transition, and we have a strong pump here, which is coupling a weak transition. The 6p state is a weak state. In other words, it's a weak transition. The absorption of this transition here for the laser is about 20 times less compared to this IR transition. And therefore, this is very strong. This is very strong. And that, we always opt to do measurements at room temperature. And if we could have used, for example, some other techniques, such as saturated absorption spectroscopy, we end up with some problems because detection of transition here is usually a challenge because it's a weak transition. Therefore, you end up using high intensity. As a result of that high intensity, then you can be able to detect something. But at the same time, you have to hit your sample, that is the vapor cell. The vapor cell has to be hit. This is to post the atomic density within the vapor that is participating in the interaction. And this will enhance what you call absorption. But as you post the signal, it will be improved. At the same time, you run into some. In the process of heating your cell, if it is not heated uniformly, you find that at the edge, because you, for example, you heat it along the length, then the beam starting from this cross-section, and then you are detecting on the other end, this cross-section area is usually at a lower temperature compared to the length of your sample, length phase. Now, as a result of that, the rubidium atoms start on the collar surfaces, That, in essence, makes the cell to be opaque, then blocking more light that is entering the cell. And as a result of that, the signal-to-noise ratio, you were improving, you end up making it even more worse. But that's not the only reason for that. If you eat the atomic cell, you are increasing its temperature, then you also make its velocity, that is the atoms, to move much faster. As a result, you increase what we call collisional, there will be atom-atom collision. And as a result, when you are doing it, you encounter what we call collisional shifts. So these shifts have to be, or the pressure shifts, this has to be accounted for while you are doing your measurements. And as a result of that, that is why we normally experiment at room temperatures. But at room temperatures, the absorption of this Prout transition is very low. And then, because of that fact, that is why we are opting for this double resonance. In other words, we measure absorption of this Prout transition using a strong transition. This is reverse. We are not directly detecting it, but we indirectly detect it. Absorption of IR transition is very high, and therefore this inverse detection, because now we have to log this IR laser at resonance, and therefore, once it's locked at resonance, we keep its absorption flat. So this right changes if the absorption of this IR laser is as a result of the absorption of the blue laser. Then, once we do that, if you scan the blue laser across this 6p state, and since they share a common level here, for example, then this IR probe will be removed because of the coherence effect that is causing electromagnetically induced transparency, that is EIT. And as a result of that, probe absorption reduces at the line center, but anywhere resonance, and probe is simply addressing only zero velocity group atoms, near zero velocity group atoms. We also have another technique here. And that technique is what we call enhanced absorption. For this technique here, lasers do not share a common level. They appear as if they are disjointed. Each one of them is just like, for example, having two-level system that are disjointed. And therefore, because of the pump or the laser will pump atom from the lower ground, and that will be the laser on the upper ground. So in other words, this blue transition here, the blue laser, will take the atoms to the excited state, and then they decay back either the same ground where they came from, or ground, because there's options. And therefore, the ones that are decaying to the upper ground will be detected by this probe laser here, and that is why we have this enhanced absorption here. For this enhanced absorption here, this can be theoretically be analyzed, and you can see that we only have one part here, population difference in the ground state and the excited state. But since we also have into picture, then this population difference here in level 1 is as a result of what is decaying to this level here. Similarly, deep here, which we have said there is coherence that is causing HIT, is also contributing to that. And there is also population transfer. Now, we could have expected that this line, because we have locked our pump, our probe to resonance, we could expect that the line width will be much smaller. But that is not what we observe in the experiment. We observe very large lines. Very large lines. But before we discuss that, then let us go to the experiment. How does the experiment look like? This is a typical experimental setup. For this experiment, you have the blue laser. You split into two parts. One of the part, you send it directly to the cell, and the other part, then you process it. You take it, shift the frequency of this beam here using what we call the double pass technique through this acousto-optic modulator. And what does that mean? We have and we also have what we call a quarter wave plate here. And therefore, once you pass it through the quarter wave plate twice, it is polarization. Now, the polarization, the initial polarization was horizontal, emitted through these beams. It's horizontal. But once we pass it through this acousto-optic, the wave plate twice, then it will be, its polarization will change. It becomes vertical. And as a result of that, then we can have this being reflected instead of being transmitted. It will now be reflected in that case. You can also change, if you want to use the same polarization, you can also change this polarization to be horizontal, from vertical to horizontal, using a half wave plate. Is possible. But the major part is to frequency shift this. so that we can do measurement. So one, he will generate a spectrum that is not shifted. One will generate a spectrum that is shifted. Now, this is, for example, a spectrum that we get electromagnetically induced transparency, and this is for enhanced absorption. So we have the two peaks separately for the two techniques. But how do we do this measurement? That is the question. Since we have shifted our spectrum, then we shift the peak of one. For example, this peak, this smaller peak here, which corresponds to this one here, has been shifted such that it coincides with this. In other words, we shift it to the hyperfine level. That is the hyperfine interval. In other words, we are measuring this hyperfine interval between this f is equals to 1 and f is equal to 2. So we shift one of the functions to the this the same has been deliberately inverted so that you are able to monitor what you are doing in the experiment, and that is why it's the same technique, but you invert one because if they are facing the same direction, sometimes you are doing the judgment, you might not exactly see where is the peak of the other one. So when it is inverted in that form, one is inverted, and therefore it is easier for you to monitor that. But why are we not making a single measurement so that we shift it exactly to the hyperfine interval, and then we do that measurement? That becomes very because of that uncertainty principle. You cannot precisely measure it. And as a result of that, we have to shift it across this peak here. And then, once we have enough data, then we can do this kind of graphing, and you can also determine how far is your data from the mean. And with that, if the shift is 0, that gives you the hyperfine interval that you are measuring. And from there, you can also do the calculations, for example, of the hyperfine constants and the rest. Now, the line that experimentally, the one that is using electromagnetically induced transparency, was ranging between 29 and that one. The line that was measured experimentally, the enhanced absorption was ranging between 31 to 34 megahertz. But what is the line with excited state running that much? One, it is easier to see one of the factors is because of wavelength mismatch. Because this is at, for example, at the experiment was conducted in at 780. So let us see that. Yeah, this experiment was conducted at 780, and this is 420. So because of the differences in terms of the wavelength, that causes what we call partial Doppler broadening. That is, the wave vectors do not go completely. In this case, this is what we see. If K1 is not equal to K2, then these differences here will add up as you are scanning, because the scan of this one is 0 as you scan. So this is going to cause what you call partial Doppler broadening. So it is easier. And for example, if you have the two wavelength matching, then you have the red one, which where 780, it's also 780, then or 794 for the, then you have the red curve, which has a narrow line compared to the other one, the blue curve, which has a broader line, and that is because of mismatch. The other factor, we have theoretically demonstrated a rigorous way. The work actually has been done by the who are doing the masters, and in a very rigorous way to demonstrate this. And then, in order for us to demonstrate this, we make some assumptions. That is, for example, look at the phase system, which is the double resonance, such that now we are addressing what you call cyclic transitions, whereby all these excited states decay to the same ground state. Then we have another part of the system where this IR is decaying to the same upper ground state, but the blue one is transferring some population to the lower ground. But at the same time, we can allow this one also to decay to the lower ground, such that we see what is the difference between this system and this system here. And as from the calculation, this system and this system here, there is no difference. Why? Because of the fact that the probe that we are using is very weak. And in that beam, this probe doesn't transfer population. As a result of that, then we expect that this spectrum for this transition, for this system, and that is exactly what has been matched in this case here, whereby we have the blue and the red matching, having a very thin difference between them. Very tiny, but that difference is quite negligible. Then, for this system here, we have the black color here. But at the same time, so you can see, population transfer from the IR racer is what is causing this population here. I mean, the broadening of the spectrum. This is because of the fact that you are losing atoms from the interaction site. These atoms that are decaying to the lower ground are not for interaction. And as a result of that, this ground, which is not coupled by an laser, it appears as if it's a dark state. Atoms are being lost to the lower ground. And as a result of that, this leads to broadening of the spectrum. Just like, for example, you have students who are moving out of the class and they don't come back. Eventually, when you do the increases for those students who are away from lectures and who are present, if all of them they were present, failure rate is lower. And that is what we can picture in this case here. In order for one to compare this system here with this one here, then with this system here, we have allowed, because the beam that we are using has a finite diameter, and therefore atoms are getting into the beam and also getting out. This causes what we call defacing. And as a result of that, we allow defacing, ground state defacing. We include it in the calculation. And therefore, to compare them with this one, then you must also allow some, that is, beams getting in and out of the beam. And therefore, we allow the ground state here. But the atoms are not decaying to the lower ground. And that is what is giving us this part here, the red curve here. And the green curve, this one here. The blue curve here is for this curve here, for this system here. Then you can see that the major culprit in that is causing broadening of the spectrum is nothing but optical pumping of population to the lower ground that is not coupled by the laser. State that is coupling those atoms. So they will stay there until you have a laser that is coupled to the lower ground to bring them back to the interaction site. Yeah, so that, but the question is this all? Are these the only broadening mechanisms in double resonance? To answer this question, we shall look it at the end and see what the students have done. This just as part of what they are. And then, in the end, we shall see what they have done, which we have had it's not been there, and something else on solving closely spaced lines. And rubidium, which have hyperfine levels which are closely spaced. For example, the hyperfine interval here is around 30 megahertz. This is 20 megahertz, and this one here is 39 megahertz. So this is 85, rubidium 85. So if you want to resolve this rubidium 5 using double resonance, which we have seen that you can conduct this experiment at room temperature, then you have a line width of your spectrum that is ranging between 29 to 34, and you have an fine interval of 10 megahertz. It becomes impossible, very difficult for closely spaced lines. And what we are discussing here accident. Sometimes would accident in a lab. And if you are not very careful, you might miss that accident. While you are doing some on something else, you find something else is popping up. And this is one of them. In the lab, we were doing Doppler resonance, that is the IP measurement, which this experiment here. And for this experiment here, we had a single rubidium cell. And it is the same cell that we are doing measurement. It is the same cell that we are doing the locking of our IR laser. So I arranged these beams so that we have saturated absorption spectroscopy for locking the IR laser. And therefore, at the same time, the other part is doing the measurement. So these beams started interfering. As a result, you observed a dip. We tried to move the cell to remove this dip, but it was becoming very difficult. So in the end, my supervisor into this problem. Why are we having it? So I had to have some experience from the two-level system, and that is why we came up with this system here. Now, velocity population oscillation. This population oscillation depends on the velocity of the atom. And as a result, if you have two beams that are following the same transition, for example, this IR prop and this is IR pump, both are counter-propagating. They will have different Doppler shifts. And because of these Doppler shifts that is exposed to each other, since these two beams here, they are having same polarization, they will interact, so they will start to pit. So the pitting of these two beams will cause what we call population oscillations. And the pit frequency will be provided by the velocity of the atom. IR laser and the IR laser are counter-propagating, but for this case here, the Pru laser is co-propagating with the prop. And therefore, the pitting is between these IR lasers, that is the ground state and the excited state. This is what is causing population between the ground state and the excited state. Now, the response of this atomic system to these oscillations, because of the interferences, you have high intensity, low intensity, when you have interference between these two beams. So you have where you have maximum intensity, low intensity, maximum intensity, low intensity. And as the atom is traversing through this region, the variation of intensity, the population will follow the variation of intensity if and only if the bit frequency is such that it is less than the inverse of the lifetime of this excited state. And for that part, that condition is stated here clearly. The frequency and the bit frequency, which is twice kV, whereby V is the velocity of the atom, K1 is the wave vector. So that, twice that must be less than the inverse of the lifetime of that excited state. And there is also another condition. This lifetime for the excited state in the blue transition should be much larger compared to the lifetime in the IR transition. If, for example, you make of this to be equal to this, the dip disappears. And so that is one of the conditions. Therefore, this has to be much larger compared to the lifetime of that excited state. And for this velocity of the atom to respond to this splitting frequency, the velocity of the atom should be near the zero. What does that mean? It means that the response of the dipole has a mass. It also has what we call inertia. So in this response to the bit frequency should be such that it is within the lifetime of that excited state. The lifetime of that excited state. For large velocities, it will not work. And that is why this technique here is only for near zero velocity. In other words, you are targeting atoms which are moving perpendicular to the beam. If this is the beam, then you are targeting atoms which are moving perpendicular to the beam, not at large angles. At large angles means they have very high. So the ones that are moving, they are the ones that are this bit. And then we also asked, can we enhance this further? Because after doing this experiment, we found a limitation. This dip that we observe here is usually very large compared to what we could have expected. As a result of that, okay. So we did what we call some counter-propagating also the blue, and that is to introduce the effect of velocity selective saturation effect, and that enhanced further so that this is the various results that we obtained. One, we have the saturation effect, we have population effect, population oscillation, the result of the population oscillation, and then we have the result of the coherence. Dip that we are red here is as a result of two factors. One, there is coherence effect. There is also population oscillation effect. And this is due to the strong giving us the for the green curve here. So this is when you analyze it element-wise to see exactly what comes out. The same case applies here, and for this we can get an enhanced dip. And for this we have population oscillation here, so we have narrowed this, and therefore line width of this is actually before you extract the broad background, then the line width of this one is about 15 megahertz. More from 31 to 15. The line width of this one here is around 11. And if you subtract the background, you find that the line width is going to narrow even further. This is for the enhanced absorption, and it also has, for the enhanced absorption, you have this coherent population oscillation. You also have this pitting. I mean, you have a saturation effect and also pitting. There is no coherence for enhanced absorption. And for that, we can be able to enhance it further using saturation effect. And if you use saturation effect, you can see that there is a dip at the Pru transition, and that dip is as a result of saturation effect on the Pru transition that enhances the dip further. And that is what about this dip here being even much narrow here, and here is. In other words, you are having the two processes because they are near zero velocity group atoms. For the near zero velocity group atoms, you are now having power management at your ends. You can manage power product at your ends. That is as a result of the intensity of the beams. This is the experimental setup. I will not go to the details of that. And this is the experimental result. And one thing here, this is using velocity-induced population oscillation. And you can see that the peaks here are slightly much broader compared when you have velocity-induced population oscillation and velocity-selective saturation effect. But there is also a difference here. This is the same as this, but you can see there is a difference in terms of the line shape, and this is because of the fact that this experiment was done when there was no shielding to the vapor cell. That is because of the external magnetic field that brought to the broadening of the line, and that is why these lines look much broad compared to this one here. So we noticed that, and then we had to use a magnetic shield to shield the cell from an external fields. This is for the enhanced absorption, and you can see that we are able now to resolve closely spaced lines for rubidium 85, and this interval here is 10 megahertz. But still, if it looks very closely, you can see that still there is a struggle here in resolving this. The peaks are very small. There is a struggle. And with that, this is for rubidium 87, and you can see that we are able to resolve that very well. And lastly, I want to talk about the application of this effect of coherent population oscillation. Sometimes in an experiment, while you are working, either you are doing your laser cooling experiments or precision experiments, and you have locked your laser, then the question is, how precisely is your laser locked to resonance? How precisely is your laser resonance? And you want to monitor it in real-time situation because the laser keeps on drifting. The frequency of the laser keeps on drifting because of mental conditions, like for example, that will change the color of the laser, and therefore it causes a change or the tuning of the frequency. So the question is, how precisely is it locked to resonance? That is what is giving us what we call a lock offset. And to see that, then we are using this coherent population oscillation or velocity-induced population oscillation. This dip is very sensitive where the laser is locked. And therefore, in experimental results, not go to the detail setup where we locked the laser, its frequency shifted, and we are using the double resonance, the double pass. That is for accuracy of, as you change the frequency, then you don't cause misalignment of your experiment. And for that, this is locked, it is downshifted in locked at the cross, so that this is locked. I mean, the laser that is going in this direction, is locked at resonance. Then, by changing the frequency of this OIM, the laser is going to this measurement is locked in that case. Now, this is one of the calculations that we made theoretically, and you can see that the dip becomes, when it is, there is no shift from the resonance, the dip is symmetrical. But when it is shifted from resonance, it becomes asymmetrical. For example, the red one is 2 megahertz above resonance. It is the blue one, it is at 2 below resonance, and you can see the differences. And for this one is at resonance, and therefore it becomes symmetrical. And you can also determine how far can it move, how far can it move and do such kind of fitting. How far can you move in terms of away from resonance? So this is one of the typical experimental experimental results, where we can tune the laser on resonance or away from resonance, and you get this kind of spectrum where the dip can either be symmetrical or asymmetrical. And if it is symmetrical, then it means that your laser is at resonance. Lastly, what do we do at NIOL? What are we doing here? So let us look at the work the students are doing. And one of the work that they have done is to determine what are the other factors that causes broadening, or the broadening of the line in the dipole resonance. And as we have already seen, we have looked at wavelength mismatch, we have looked at optical pumping of operation to a dark state, and the other one is the lifetime of the intermediate state. Now, these intermediate states here, these are some of the intermediate states. So the atom that is excited from this ground state 5s can go to the 6p. We have 6p 3/2 here, 6p 1/2, and 3/2, and 6p 1/2. So the atom has the option to either decay to the ground state or decay through these branches. So those options are there. And suppose these intermediate states here, they are cool. Takes longer time to reach the exact ground state. As a result of that, you end up losing atoms to the metastable states. That is what is called this broadening here. We did a deliberate analysis so that we can be able to vary. For example, if we hypothetically, let us vary this lifetime of these intermediate states. Then we find that line broadens to the blue ones, which is much larger, about 36 megahertz. That is very large. And therefore, this is also contributing. If you are doing an experiment and there are other intermediate states in between, then what is the lifetime? The lifetime of those intermediate states, they also contribute to the broadening of that line. So that is one of the parts that they have done. And the other part is a line alloy of using the triple resonance, because the double resonance has been exhausted, and therefore can triple resonance narrow these lines further. And for that, we look at the N-type system, and precisely we target what we call counter-propagation configuration of the IR laser to target only the near-zero velocity group atoms. And for that, we see that for zero velocity group atoms, we have this kind of behavior where if you change the intensity of the pump, that is the intensity of this pump here, the IR pump, then you have this kind of figures here, and that shows the various transition from EIT to EIA. And the small peak that you see here is not small, it's large. This is for Doppler averaged, that's how it looks like. And you can see that this dip here is very narrow. And the line width of this dip here is around 9 megahertz. That is even with the broad background present. And for this part here, the peaks are even more feasible and they are very large. So if you subtract the broad background, then we aim to reduce this to even much smaller, closer to the natural line width. That is how low that we want to move in that direction. Lastly, there is also another student who is also doing this part here, where we are asking ourselves, what is the source of this dip that we are seeing here? What is the source of this dip that we are seeing here? Is it because of the fact that we are having population transfer? Is it that reason? Or is this because of something else? And to do that analysis, done this kind of a system whereby we now have only population transfer. There is no coherence. It's only population transfer. And the question that we are asking ourselves, is population transfer a sufficient and necessary condition for us to have this dip at the line center? And the results are the opposite. This population transfer can only narrow the spectrum. It's only narrowing the spectrum, but it's not creating the dip right at the line center. That means it is necessary, but it's not sufficient. The other part, we analyze only coherence. There is no population transfer. Then we make this part here to be a cyclic transition, such that there is no population transfer to the lower ground. And since our probe is also weak, this probe is also weak, then the probe doesn't transfer as much population to the ground, to the lower ground. Because if it's transferring population, then there will be population that is going to the lower ground. But since it's weak, there is no population transfer in that case. And then the results turns out to be positive. And in fact, the peak becomes larger. What you are seeing here is even larger to what you seeing in this case here. Which means that this dip or this peak at the line center here, the dip on the is as a result of the coherence effect that is causing electromagnetically induced transparency, not population transfer. Is not actually playing any role in creating this at the center, but it is making the spectrum to be even much, much narrow. And with that, we say thank you.
Thank you. We have time. The question, please.
Question, if you have a question, let us not stop questioning. Because if you stop questioning, it stops. And that is why we have to ask as many questions as possible, such that we learn something.
Okay, thank you so much for that. It's a good one. Now, I didn't get about the deep, please. I see there's some graphs where I can see some dips. Can you be able to explain to us why is this that there are some dips and the others don't have dip? Oh, that dip there.
Which dip? You mean this here? Oh, let me go through this because of time. That is why I rushed through this. Initially, we had the red curve here. That is when we have this pump here being very weak. This pump here being very weak. In fact, the weakness of this is closer to that, or is the same as that of the prop, so that it doesn't transfer any population. So what does that mean? It is as if we have a feed system. So this system is a a 4-level system that is behaving like a feed system. This is why we have this red curve here. So it matches that of our feed system. Then, if you try to increase the intensity of this IR pump slightly by a factor of 10, then you are increasing the coherence effect that is causing EIT. At the same time, you are also pumping those population from the lower ground. And therefore, that is why absorption on the wings is trying to narrow down. Remember, it is very wide, very high, but the wings are becoming lower, meaning you are repumping the population back, and that repumping, as I had already seen, it causes what we call narrows the spectrum. It narrows the spectrum. So that is why he's trying to reduce at the wings, and at the center here trying to rise. And this is a scenario of the competition between the EIT, but longer is still weak of 10. And then if you increase it further, you get the green one. You get the green one. And for the green one, you can see that there is at the center here. This dip at the right center here is the EIT dip. At the wings here, the absorption of the prop is reduced. That is because of courtesy of repair. The EIA effect is also increasing, so it's catching up. Factor of 10, even further, then the EIT effect becomes weaker. Coherence that is becomes greater compared to the coherence that is causing EIT. And as a result of that, because the coherence that is causing EIT is on the Pru transition, this Pru transition here, if you compare this Pru transition here, since we are not changing the power of the Pru transition, and therefore it's fixed. So we are only changing the coherence here between these two ground states, which is causing electromagnetic. You can re-establish it back by increasing, for example, if you increase this Pru pump and fix this one here at the point where you have your dip here, this dip here, you can still re-establish it back. And the absorption then again starts to become even much broader than what we have in this case. I hope I've answered your question. Another question?
Okay, there are no more questions. Let's thank the speaker again. Before to come to coffee break, we want to give the certificate to the winner of the poster prize. We already had the ceremony, but to give them the certificate, I will call them here. They already know, of course. For the first place, we will a chain. Let's congratulate again the winners, Sandra. Congratulations again. Let me say the certificate. This is to certify that Sandra Achien received the award for the best poster presentation, first place, the title of the presentation, and the certificate is signed by the director of the ICDP, Asi Dabok. For the second place, Kuntal Teto. We congratulate again. And also the play was Mora on the. Let's go congratulate Anna and give her certificate. And now we have the coffee break. 10 minutes, please, before coming to the next section.
The future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks a common language, science. Basic and applied research are both vital for society, from fundamental particles to black holes, climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their career. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies. This is the iMac lab that offers editing skills and use of iMac computers with various video editing softwares such as Final Cut and many more. This is our engineering lab, where we conduct evaluation of hardware equipment and software troubleshooting and fix technical issues. This is our physics and chemistry lab, where most practicals happen, including tests on materials, and present research findings to scientists, ensuring safety and quality standards are met.
computer lab, also known as surveyor lab. This is where computer classes take place and most of the computers are stored with internet.
Our laser optics lab, which deals with laser and optics, including transmitting and manipulating laser beams or any other forms of laser light. Welcome to our review. We have our own that to the citizens and people at listen to the sweetness of on 99.9 FM and learn more from our students as they bring to you more shows.
Check 1 2 testing 1 2
Directly help
testing 1 2
acquire communication
1 2 testing
readiness to join
mic testing 1 2 check check 1 check 1 check 1 check 1 check 1 2 mic check 2 2 thank you checking mic
A laptop is an essential aspect.
checking mic testing 1 2
Many of them are lost as a result
iko sawa
of theft,
mic mic iko sawa
but now comes the tracker, an online system that
yenye iko pale mbele
to register various electronic devices using the serial number. To access electronic services, visit the website, create an account, log into the account, register the device serial number.
check
In case
1
it is
2
stolen, you report in the portal. The red tracker will then help you
testing
recover the device.
3, 4, 5, 6.
yes test it
1 2 1 2 mic check 1 2 1 2 1 2
keep the test
Keep testing. Keep testing.
testing yes check
Microphone.
1 2 testing check 1 2 1 2 thank you audio testing 1 2 audio testing 1 2 sound check
So you don't want anything that is reflective on your, not even a watch, because otherwise it has reflection, are not controlling, and it can be dangerous. Okay. Right now, as I said, this one is not
1 2 3 4 5 6.
another, but
Sisikii sauti bana. Sauti.
important that you work
Sisikii
in a safe
sauti.
way. Let's take our cylindrical
Sijisikii
lens.
hata.
So I'll show you
Ndo
the
sasa.
cylindrical.
Nice.
Maybe you can have
Nice.
a look. So you see, it's,
All right.
I don't know if you what
Sorry.
I want you to see.
What?
Here it's black.
1 2 3 4 5.
This
Keep
side,
changing.
can
Keep
you see
changing.
that it's like a cylinder?
Umerudi
Yes,
chini.
but can
Okay,
you see
sawa.
that it's,
Pump
it's
kidogo, pump kidogo.
in one direction.
Pump
You
kidogo.
can see, right? Okay. It's quite
Pump
obvious.
kidogo. Sawa.
Can you
Sawa.
see? So,
Sawa sawa.
the thing is also, you would say,
Think
well,
tuko sawa.
it's not that easy to clean.
Sawa sasa.
You need the tools and then specific products, and sometimes some of the optics have coatings that you can damage if you. So, for example, if you have a dielectric mirror, like the one that you were talking about when you know the other lady that was talking about compression with the dichroic mirrors, with the
Check
multi-layer
2
mirrors.
testing 1 2
Mirrors are really expensive.
1 2 mic check
Get them, like, you don't want to
Mic testing, 1, 2.
Stay away from my diagram.
Mic testing, 1, 2, 2, 2,
I mean, you might
2.
compression of your passes, so it's really something
Check,
that,
1, 2.
you shouldn't do. Well, now it's done.
Thank you, 1, 2, check.
Exactly. So I'll show you. So if I mount here, this lens, okay, this mounting that I have placed here, it is a mounting that can rotate. Okay. So let's see what happens.
How do you hit maze without calling me?
Okay. First of all, let's check with a piece of paper. So we check in a controlled way. So I'm here. I'm very close to the lens, and there is nothing to see. I go in the focal plane. Look, I have. Can you see? So the focal plane of this lens, it's a spot. It's a single dot. Here, the focal plane, it's a line. Okay? Why is that vertical? Here it was round, here it's round. Here it's horizontal, and over there it's vertical. First of all, if we think of this in 3D, it's a plane. Look, you can see the plane if I do this. Can you see that it's a plane? Okay. If I rotate the cylindrical lens, so I'm rotating it, you can see I can rotate the beam. Okay, now it's vertical. If I do like this, you can see even better, probably this is a plane. Can you see? Okay? In the other direction now. Okay? So if I rotate while I move, you can see. I have a trick. I will show you my trick. My trick is use, I'll show you later. Yeah, it's a nice trick though, so I want to show you. Let's go on. How large is here in the focus? Somebody can read. Yeah. Are you sure? Okay, so then you tell me, okay, so how large was it here? No, then it has to be the same. Because what the cylindrical lens does, it squeezes in one direction, but the other one is left untapped. So the height of the beam is the same, because it doesn't do anything in one of the two directions. So now let's look at the propagation. What do you think is the thickness here? It's 0.7. Do you want to check? Come and check. So I have to say that it's 7, no? It's 7.
Yeah, it's 0.7.
Yeah, it's 7. Otherwise, physics doesn't work. The 10x object will magnify 10 times, and it has a 0.28 numerical aperture. Do you think this is a large number or not? It's not. It's not. A good 10x is 0.4 usually. At least 0.3. Come on, this is 0.20. Why? Well, this objective has the pro. It has a big distance. So the focal length is very long. So this gives me the opportunity to mount in a three-dimensional manner my sample. So I have space. I don't stay here very close to the objective. I can have something that is very big. If my sample is 1 centimeter, I need to be able to the sample. So I want to have room. If I was using a very high NA objective, I would have a better resolution, but resolution is not everything. Because maybe you want to see a large field of view, which is usually what I want to do. Larger field of view. Anyway, so what I do today, I told you that the objective has many lenses inside. Why? Exactly. So all those lenses are needed, okay, to have the right magnification, to collect as much light as possible, and to correct aberrations. In particular, chromatic aberrations. So this is a planned objective. Apo stands for apochromatic. It means that it's corrected for a broad range of wavelengths. Still, if after this I put a lens that is not corrected chromatically,
I mean, this is useless, right? So this one is not a single lens, it's not a thin lens, it's not a small one, it is a triplet. It's probably at least a triplet, meaning that it's at least 2 or 3 lenses all together, put all together, so that chromatic aberrations are corrected. Okay? So you will have to put this, the tube lens, after, okay? And then the camera. This object put at the focal from the plane. Okay? After this, maybe it's just a single lens. What happens to the light? I told you already what is going on after the object. It's collimated. Okay. So where should I put this lens? Does it really matter? And the factory who makes this tool, makes this, tells you, because otherwise, well, you could experimentally find it, but it's easier to check online. So I can tell you that the right range is from 7 to 17 centimeters. And what you will see is, as an effect, you will start cutting some of the frequencies of your light, and you will have an effect. Okay. There is a mirror mounted inside here. Okay, now I don't care, I'm not going to attach it. So, do you remember what I asked you today? So what I told you today? So if we have a beam, a mirror, okay, so that's it, fine. So what happens if I rotate the mirror now? This is a lens of 50 millimeters focal length. So over there, it's really divergent. The question is, what happens if I rotate the mirror now with the lens in front of it? Who knows the answer? Yeah? No. That's not what I wanted to do here. Okay, this rotation, when you go to when you use a lens in front, will become this to my head. Yeah, perfect. And now start moving very quickly. Okay, quicker. Means that if I rotate this mirror at the focal plane of my objective, I will be able to rigidly translate the light sheet. So this is why I want to have these 2 mirrors and these 2 lenses, to have a degree of freedom to position with a micrometric precision my light sheet, okay? Because we said we have to position it so that it matches the focal plane of the detection objective. Let's see what happens. I will do the drawing again. We don't need the first mirror anymore. So here we have a lens. Here we have our objective. A rotation here makes a translation there. And at the focal plane, we will have a rotation. So I will be able to rotate the light sheet, okay? So that if the light sheet is tilted, I can compensate for that by rotating the mirror. And I can do that both for the horizontal plane and the vertical plane. Yes?
One.
This one, they will be the same focus length, okay?
Let's restart the section, please.
No. If actually you need both, otherwise it would not work. Yeah.
And then this one dependent on this lens.
Yes. So this lens do. The angular displacement that you have here, the rotation here, is the same at this lens. Okay. Any other question? So this this system is collimated in one direction, but in the other one, it's not. Okay, it's focusing here. To remember this. Next time, I hope that we will have some.
Let's start the session.
All right. See you.
It's an honor for me to present Dr. Malik Massa. He will, Dr. Massa is UNESCO Africa Nanoscience and Nanotechnology Fellow of the Presidential Mapungubwe Order, Academy of Science, Fellow of the Royal Society of Chemistry of London, Fellow of the National Academy of Science of India, Fellow of the New York Academy of Science, Fellow of the European Academy of Science and Arts, Fellow of the Islamic Academy of Science, Fellow of the American Association for Advancement of Science, and Editor-in-Chief of Nano Horizon. Therefore, the title of the presentation is Nanophotonics for SCDGS, Science Benefiting Society. Then, Dr. Massa, the floor is yours.
Thank you, Program Director, senior and junior colleagues. Allow me, please, to express my gratitude to the organizers for their kind invitation in associating us in this endeavor. I would like, if you allow me to do so, Umberto, would you like just okay, that's okay. Yes. So my colleagues and the various lecturers went through a number of advanced photonics techniques and laser-based techniques in terms of fundamental investigations and so on. What I would like to do is a little bit move on another landscape. I would like just to share with you some of the potential applications of nanophotonics and also the engineering of these nanophotonics using laser-based techniques and using a massive set of characterization techniques in view of giving them functionalities that can be used in health, in water, in energy, and so on and so on. And I would like to share with you these examples, colleagues. And the title of my contribution of today is Nanophotonics for SDGs, Science Benefiting the Society. It's not necessary to do fundamental science, but it's extremely important to show that the science that we do have an application. And I would like to share with you some of this application in this regard. This talk is given within the framework, as it was mentioned by Umberto, within the framework of the UNESCO Africa Nano Chair. The UNESCO Africa Nano Chair is a bilateral partnership between the UNESCO plus Fontenoy in Paris, the University of South Africa, the largest university in the African continent, 450,000 students. It has 9 campuses in each of the provinces in South Africa, and it's the unique African university which has a campus outside South Africa, outside its borders, that is in Ethiopia, following a memorandum of understanding and an agreement with the African Union. And of course, Itamba Labs, which is a national facility of the National Research Foundation of South Africa, and one of the fellows here, Moses Juma, here present, is a part of this UNESCO chair. And I must admit the Kenyan education system is extremely robust and high quality. The UNESCO chair has 2 major centers, one in Cape Town. I'm really failing to use the laser. One is in Cape Town, the largest one, and the other one is in Johannesburg and Pretoria. The outline of my talk today, and certainly I will not be able to finish all of it, but certainly I will concentrate on 1 and 2. I will share with you some of our application of nanophotonics, which were made by laser-based techniques, and their application for water decontamination, for solar energy, for smart windows, for coatings for satellites, and other applications for health. And I will go to the second one, which whereby I will share with you something which is really interesting, somehow, which is the materials for nanothermochromic materials for smart windows and green air conditioning. And the third one, hopefully, if time allows, tomorrow or during the week, I will share with you a concept that James Clerk Maxwell, the father of electromagnetism, came with, and to synthesize what we call nanofluids. Fluids which are capable to remove heat far better than any ordinary we do use currently. And the fourth example that I want to share with you, colleagues, is the example of strong Anderson localization. One of my colleagues, I think in the last week, have discussed this aspect. And if time allows, I would like just to pay tribute to, for the last example, to Abdus Salam, who is the father of the standard model. And it happened that we managed to use nanostructures, Fabry-Perot resonator, to trap neutron and to measure somehow its lifetime, which is related to the standard model. Allow me please to go to number 1. The field of nanophotonics is the field of, it's a multidisciplinary field, physics, chemistry, engineering, computational, dealing with materials at the nanoscale. Their size is a nanometer. To give you an idea what is a nanometer, you take 1 meter, you divide it by 1,000, gives you a millimeter. You take a millimeter, you divide it by 1,000, it gives you a micrometer. And you take that micrometer, you divide it again by 1,000, it gives you a nanometer. In the past century, we were operating at the micrometer. But currently now, we are capable to operate at the nanometer. Why? Because there are possibilities or technologies which are capable to allow us to make these materials at a nanometer scale and to manipulate atom by atom and to create from bottom up to create nanomachines. You would understand that in the past for us to store one MP3 song, we were not able to do it because we were using very large discs of 20 centimeter over 20 over 1 millimeter thickness. And for currently we have USBs which are terabyte. How it comes that we cannot store using a very large device to store an information and we were not able to put an MP3 song, and now we have USBs which are very small but capable to store a large amount of MP3s, movies, whatever. For the simple reason is that now, before we were storing the 1 and 0 on a surface, on a dimension of 1 millimeter of over 1 millimeter, we gained a little bit in terms of space, where we can store the 1 and 0 over 1 micron on 1 micron. Now we are capable to store on 1 nanometer or over 1 nanometer. You do understand why the USBs of terabyte, how they operate, because we were capable to make materials, at the nanoscale. And It is just a normal, can somebody help me please with this for the laser pointer? I have no clue why it's not working. Ah, sorry. Sorry. Errare umano, persevare è diabolico. Okay. Okay. Well, there are probabilities now. I think I'm checking the theory of the first speaker. Blinking, you know. Anyway, colleagues. Anyway, colleagues, Mother Nature operates at a millimeter or even, and when you go down to the red cells, they are submicrons or a micron. And when you go completely at the bottom, really the building block, it's the DNA, that pink stuff there. The DNA can be extremely, very, very long, but it's the basal, the dimension of its thickness is in a nanometer. And therefore, the building block of any living species starts from the DNA. And that's exactly what the strategy that humanity or the scientists have adopted, in particular Feynman, when he by the century we will be able to make material nanoscale and give them a in the past we were with the fiber optics like this. That was the smallest dimension that we were make. Then we went to submicron, and we are now at scale where we nanorobots, nano devices at that limit, at that level, which is more or less a copy conform somehow of what Mother Nature does. So we are moving from bottom up. And colleagues, what happens and what is extremely important when it comes to materials at the nanoscale. So the binding, if you have a molecule that you want to bioconjugate with these particles, the interaction can be extremely very strong relatively to the bulk. And therefore, for example, if you have an anthrax in water, for example, you may use gold nanoparticles, and the anthrax interacts extremely very well with the gold nanoparticles, and you can detect and you would identify that there is anthrax indeed in that water. In addition to in particle, for example, if you have the silver nanoparticles or gold nanoparticle, you have free electrons. Remember that we know that you have free electrons. But these free electrons, no more particles at all. They behave like quantum mechanic behavior is dominating in this case, and therefore the properties of materials do change. In the case of gold, if a gold is yellow when it's bulk, it can be green, it can be blue, it can be red, and so on and so on, depending on the size and the shape. And this to make also at the level of in the case of nanomaterials, that shape pivotal controls the properties, the macroscopic properties that we how can I say, as I mentioned also, you will of gold, I will show the typical case for such. Colleagues, nanomaterials, you can find them in different forms, either spherical particles, independent particles, or particles embedded in a matrix, or you can find them like nanotubules here. Nanotubules or nanorods, or you can find them in a form of thin films. They can be, the dimension can be centimeter or even more. This transmission is less than 100 nanometer, and therefore it's nanomaterials. Of course, you can find them in a form of multi-layers. Also, the optics that you use in any lab in optics does have this kind of materials, or these ones. This is in a real world what you have. A colleague, polystyrene nanoparticles that we use to filtrate water, and these are cubes of platinum for anti-pigment, and here are silver nano lozenges, triangles. And you have also carbon nanotubes and the zinc oxide nanobelts for photoluminescence screen. The flat screens that we currently, the red color and the blue color, the different colors that we have on our flat screens and cell phones are not red particles, whereby we control the shape and the size. As I have mentioned, colleagues, the gold bulk, it's yellow, but when it is, how can I say, nanometric, small, in extremely small, it can be, you can tune their color, and if you can change their, and tune further their color, and the same applies to whitish, and it's in different colors like that. The field of nanosciences and nanotechnology, colleagues, it's exactly as it materials. Photonics are material-centered, but they are applied in each sector, and it's highly and the most funded worldwide. In effect, the funding of the nanosciences reaches nearly $1 trillion per year globally. Colleagues, it brings me to the point of, how can I say, of this talk is that the you photonics with the properties are all of them are related to applications sustainable development goals. If you are not familiar with that, I beg you please go and read, because the United Nations have defined 17 sustainable development goals. If each of us contribute in a way or another to one of them, will definitely recover a healthy earth and an equitable humanity somehow. The first one is, of course, poverty. We are not in all of them, but I will single out this one, and I single out this one, and this one, and certainly this one, just to convince you how we can make a difference. And how can I say? Yet you may think that you are not in the field, but I can assure you when you go a little bit to dig further about what is the Sustainable Development Goals, you will find out that you are contributing in a way or another. Sorry. Well, the first case, I would like to share with you an experience on the application of nanophotonics and the usage of photonic techniques and the basic techniques to identify very effective materials. And I would like to share with you a typical case by which colleagues, you will see that share with you a case of a material that is, how can I say, it's an indigenous knowledge, which means rural area peoples, our old grandfathers and old grandmothers do know that the secret, but they have not shared it, and it has no scientific validation. And something that was so, yeah. And in this case, colleagues, always we include for each project, for each targeted project, we involve fellows from South Africa, Botswana, Egypt, and Iran, always, and there is a mix of disciplines, but how can I say, but all is geared towards photonics applications. And colleagues, a typical case that I would like to share with you is this. Colleagues, in the southern hemisphere, the skin cancer melanoma is really a major threat. Why? Because the DNI is very high, the direct normal incidence is very high, very, very high. And because, of course, colleagues, the sun is quite, yet indeed, percentage of the solar spectrum is fine, but the DNI is very high. And of course, you can see also the infrared radiations, heat generated. So colleagues, in this community of the Khoisan are very well known to have the lowest skin cancer melanoma, and if not zero. So we wanted to find out why, and if it is the case, how can we use a potential skin cancer melanoma. And well, we have found out the literature review shows that they do use extensively this plant, Hoodia gordoni. They use this Hoodia gordoni for a number of applications, but use this, how can I say, this natural extract. They boil it in water and they get that extract and they mix it with the goat milk and they put it on their skin. And well, we have had to find out to give scientific proof, and in particular, in relation to the, how can I say it, in relation to the UV radiation, UVA, UVB, and UVC. So we have synthesized, using this natural extract, we have synthesized oxide, which is number one in cosmetics, luxury cosmetics. So we have embarked in cerium oxide, and with that we bioengineered using this natural extract, and we have indeed made a formulation of a goat milk. It was not an indigenous goat, but it was goat milk. Well, colleagues, well, as you can see here, this is the response of this cerium oxide here, made by this bioengineered using this plant. As you can see, colleagues, it stops the UVA, UVB, and UVC. And relatively to the other standard cosmetic protections, this one is quite very large in terms of spectrum effectiveness. And to do that, colleagues, you would understand that we have had to go through optical methods, and the optical methods have allowed us to show that in effect the diffuse reflectance, the reflectance here in the UV, blue UV, A, B, and C, extremely very low. It's at the limit of detection, and the transmission is 0, and therefore the absorption is nearly 100%. And how can I say? And the treatment of, in addition to this efficiency of this material, not only they stop the UV, their reflection is a heavy-side type. It's a heavy-side function type. In addition to that, colleagues, this material, how can I say, we know more or less the transition involved in this and why it is as excellent. We know clearly now. And also this material, it happened that it has a low ROS. So it's not harmful to the DNA at all. When you coat the skin with this Seria bioengineering, this method, it has low ROS relatively to the protection that we use when we go to the bush or when we go to the sea. So you can see clearly that in effect the optical method had allowed us to validate scientifically an indigenous knowledge that we thought was, if we have left it like this, they will say, oh, this is a Tokolosh type science. Here, no. In addition to that, colleagues, this paper has been published in Nature Scientific Report. So it speaks for itself. And the other case that I would like to share with you, colleagues, and this is related to health, colleagues, straightforward to health. And if you try to use cream anti-cancer, very effective, they are extremely expensive. And here it's a rand type, it's nearly 1 cent dollar. But it's an indigenous knowledge. If we have not validated it scientifically, and it has not published in Nature Scientific Report, they will say, oh, it's an African tradition, what medicine. Here, no. I would like to share with you, which is related also to an indigenous knowledge, is knowledge that comes from the Himba people. These Himba people are people living in the south of Angola and the north of Namibia. And these fellows, this African community, do not shower at all. They do not shower the way that we shower. Water is scarce. They do not shower, but they have the lowest anti-cancer, and they have no bacterial infection whatsoever. Colleagues, this is, how can I say, we have had, why this community has the skin cancer melanoma, like 0 infection bacterial, yet they do not shower the way that we shower, and they live in an extremely hot location. That is the north of Namibia. Colleagues in Namibia, we are organizing an international conference in which we will have 5 Nobel laureates next year, 2025, in Namibia. We hope to see you there, and you will see the beauty of Namibia in that regard, colleagues. The same thing what we have done, we combined fellows from different photonics and material science background, and colleagues from Sudan, from South Africa, Iran, and using computational DFT, which is that they learned from the ICDP, colleagues. And these fellows engaged to find out why the community of Himba people do not, how can I say, suffer from any bacterial infection. And these fellows, colleagues, live in an extremely hot location. It can reach 56 during the day, colleagues, and -10 during the night. You would understand that it's extremely, how can I say, not livable. And here, colleagues, in particular the women, they coat, how can I say, they put and protect their skin all over their parts of their body with this red powder, the red ochre, that they take from a rocky area, and they mix it with and they put over, colleagues, their hairs. And, well, of course, colleagues, these people do not have skin. Find out what is the reason. It's not bacteria. As you can see here, okay, again, the optical characterizations, different, name it, the different techniques that we have in optics related to and interface, we have done that. But I would like to single out this one, colleagues. First of all, this coating has, as you can see, very low reflectivity in the UV area. It explains why they do not have cancer melanoma. There is no UV infection somehow. Minute, it's around 5%, even less. And better than that, colleagues, see here, that cream that they put on their body, it reflects the infrared more than 50%, which means that it protects their skin from burn. And better than that, colleagues, when you go to the antibacterial, this is the streptomycin. It's $100 a tube, colleagues, $100 a tube. And here, colleagues, when you use their red ochre with the milk goat, it has an effectiveness above of, how can I say, quite effective. Not as much, but as streptomycin, but it's high. And this is 1 cent medicine. These are the Staphylococcus aureus, and we do know why now they do not suffer from any antibacterial infection. Colleagues to go through, and I think next time you eat tomatoes, you have to think twice. It happened that it is proven always we wanted to go to further our dynamic about the cancer of skin, and it happened that we found out that lycopene in tomato, lycopene is the molecule, is that the compound here, which gives the color red to the watermelon and to tomato. And it happened that, colleagues, this compound, it has double conjugated stuff, electronic configuration, and therefore high stability. You must expect that this lycopene could present a high optical nonlinearity an enhanced Chi3. Well, as St. Thomas, we believe what we see, but we went, of course, to characterize this lycopene. I will not go through the optical stuff. The copy of this presentation is shared with the organizer, so you can, if you wish. I will not go through this. Well, of course, the major characteristics, the Raman, and here indeed we have identified that is pure lycopene. There is no contaminant. This is the of the lycopene, and the easiest way to measure the Chi3 is to do the Z scan. It's simple. It's a one beam. It's not a beam or what? No. Simple beam, and you, how can I say, you are capable to. I do not want to discuss the, how can I say, how the Z scan operates. It's an easy technique. In the linear optics, it's a really magnificent, beautiful, and simple technique, yet extremely efficient indeed. And that to calculate or derive the real part and the imaginary part of the chi. And colleagues, this is it. As you can see, the response is not the transmission. The transmission, normalized transmission, is not constant. Normally not constant, but definitely this signal here, this signal is a signal confirming clearly or validating clearly, crystal clearly, sorry, the nonlinearity of the lycopene. And better than that, colleagues, better than that, colleagues, it happened that if we take all the data which was published in the literature since the birth of nonlinear optics, you will find out that the natural extract, the lycopene, has the highest ever, higher than the chlorophyll, higher than a number of other artificial porphyrins and so on. So it tells you that yes, indeed, it's possible to use this lycopene as a PDT, yet the lycopene is not soluble in water, but it's soluble in serum and so on and so on. So you can use it as a PDT to using IR laser and converting that laser, IR laser to UV, something like this, and said to kill the cells locally for cancer treatment, for PDT. I will jump, colleagues, I will jump to something else. It's agriphotonics. Show you, colleagues, you have seen, colleagues, the price. You are feeling, you felt it in your own countries. The prices have rocketed. The prices have rocketed of food, because even if you produce locally, for the simple reason is that we do not produce. It's due to two major parameters: the transport, petrol, and the fertilizers. It happened that the supplier of fertilizer are Russia, Ukraine, and Belarus, among the others. But they are the in Kenya. You import Russian and fertilizers and so on. We in South Africa, the same thing, and all over the world we do, except some. How can I say? When it comes to nitrogens and so on, all of them are from Russia. So here we have had to find out a solution to produce nanofertilizers. And please, if you go to Nature Scientific Report, which was published, do it. Do it. Use your natural extracts of some natural plants of yours and produce it locally. We have described exactly, we have not patented it. We wanted to ensure that it's open access. Go to our papers and reproduce that one in your home country. These fellows have been are from different disciplines, but they use extensively optical methods. That is the first one from Botswana, and she is an agri. From the DRC, he is an agri. From Egypt, is a physicist, Matthias Sanst, and she is a chemist from South Africa. And colleagues, yeah, I don't go through these details, colleagues. What is sure is that I would like just to share with you, please, this one is the import of fertilizers within the years, up to 2014, but the same thing, the same thing. It has just rocketed further. It's okay, normal for Asia, North America, Europe, but see Africa, it's extremely very narrow stripe. Why? Because the fertilizers are very expensive, and therefore we need to come with a solution. Those who allowed us to go that route. I will not go through the details, but well, sorry. The market of fertilizers, just to give you an idea, at least just get these numbers, colleagues, just get these numbers. 56 nitrogen dominated by Russia, dominated by Ukraine, phosphate, part of it Ukraine and Belarus, as well as Russia and Morocco at a certain extent. But phosphate is not really the one. The one are here and that one. And here, these fellows have managed to bioengineer at zero input energy, at room temperature, at atmospheric pressure, calcium carbonate. But that calcium carbonate is so pure that you have to use an armada of optical techniques to get it right. And for such, of course, colleagues, FTIR tells us clearly that indeed you have high quality calcite. These are the two vibrational modes. Zoom on them. Clear idea that it is calcium carbonate. That is the Raman, colleagues, telling us, yes, indeed, it's a really single-phase calcite. These are proper modes to the calcite, because there are other phases in the calcium carbonate. The photoluminescence, colleagues, hinted to the process or to the mechanism of formation. I will not go through it. What is sure here are asymptomatic. We believe what we see. My mother was a Jew, my father was a Muslim, my wife a Roman Catholic. So that I use St. Thomas extensively. You can see here, these are plants of tomato, and here without nanofertilizer that we produced, with a low average, with an average with a high, and colleagues, as you can see, boom. Yes, that's the tomato with the small amount, low concentration, higher the threshold. As you can see, colleagues, speaks for itself. In addition to that, colleagues, is that we have used quite the fluorescence and other to investigate the nutrient value and the toxicity of if. Example that I would like to in the poverty, and here is SDG 6, that is water. And colleagues, here, colleagues, you would you would remember that there is a fierce, there was a potential unfortunate war between Egypt and Ethiopia, between two sister nations. For what? For the aspect of water. And therefore, colleagues, you would understand that when you see that graph here that I will be mentioning, I will be sharing with you, colleagues, here. Colleagues, these are the UNECA, United Nations Economic Commission of Africa predictions for water. The cyan bars for different countries. The cyan bars are the water availability in 1990. How can I say, the dark bars are the water availability, colleagues, in 2025, next year. You see, colleagues, the bulk of the African countries will be under vulnerability. That means there will be not enough water for everybody. Some people will not be able to. But the most difficult part, colleagues, is that these countries here, they will be under scarcity level. That means Kenya and South Africa, there are some people who will not be able to drink water because it will be so. Treat the water. That water that we use in our kitchens or the water that we use when we bath and so on, we have to treat it. We have to treat it. And for such photonics or materials which are active optically are the ones who can more or less save us at a certain extent. And colleagues, here is the material of choice to clean water is the titanium oxide. When you go to the bush, you use the titanium oxide, in effect, colleagues, cream, basic cream, to protect your skin. When you brush your teeth, you use also titanium oxide mixed with host material to host matrix to clean your teeth. What is sure is that the TiO2 is very effective, but unfortunately, if you want to activate it, you have to use UV. Why? Because the TiO2 has three major phases at room temperature. That is the bruchite, rutile, and anatase. And all of them are photoactive, yes, but under UV because their band gap is 3.2 electron volt approximately. What you are looking for is you want to, how can I say, and remember the UV in the solar spectrum is around 5%, not more. So, colleagues, if you want to use the sun, because to make UV, we know how expensive it is to have UV lamps. A xenon, not a lamp, just a xenon lamp. And the idea is to use the solar spectrum, which is rich in the visible and the infrared. 46 somehow infrared and 43 somehow in the visible. We are looking to find out or to engineer nanomaterials. We want to engineer nanotitania active in the and the infrared if possible. And for such, colleagues, we have to go to TP and to learn to do have a DFT, density or molecular dynamic, to be able to find out how can we create a defect, how can we create a level here within the, how can I say, la bande interdite band, and to have this TiO2 active in the infrared. So instead to activate it with this energy here, we will be able to activate it with a lower energy. So to make this titanium active in the UV, not in the UV, but in the visible or in the infrared. And for such colleagues, we are obliged to go and to do some DFT and to find out how we can do it to create this colleagues, really you have to change this. The ICT you have. Okay, so colleagues, how we do it? How we do it? We have to create defects. We have to create defects to be able. I should not have said that. Huh? Okay. Sorry. Okay. Anyway, we have to create defects, and these defects would allow us to create a level here within the forbidden band. And therefore, to make this TiO2 active, to be able to create ROS type elements, to be able to destroy bacteria or dyes and so on. And colleagues, for such, as I mentioned, colleagues, we said that it's 5%, while the visible is around 43 and the near infrared is 52. Therefore, let's try to go for 52. This, how can I say this? Said no, Malik, it's madness. Rien n'est impossible. Nelson Mandela said, all seems impossible until it's done. And as you will see, colleagues, nothing is impossible. And colleagues, therefore, we had to hunt for this material that can be activated at least in the near infrared or the visible, and not the UV. UV is expensive. So, colleagues, I will not go through the details of what was done. We have done the DFT, density functional theory, and the molecular dynamic. I will not bother you with this. What is sure is that we learned a lot from the ICT. Really advise you really to kind of interact extensively with complement your photonics capabilities with the condensed matter to make it really sound, and that is what we have done, colleagues. Colleagues, more or less sharing with you these slides is just to tell you that we have at last found out why and where it happened. That clearly that if we create defects on some sites, some coordination, we can really reduce the band gap from 3.2 electron volt to that. And that's exactly what we have done, colleagues. And to check this, to check these colleagues, these are the synthesized nanoparticles of titanium, and this is black, as you can see. This is whitish yellowish, and this is whitish brownish somehow. This is anatase, this is rutile, but this is defective TiO2. And this black, if it's black, that means it absorbs light. Full UV, visible, name it. Rien n'échappe. All of it, all of it. And colleagues, of course, this material has to be defective, and we have to confirm that. and you will do electron spin resonance. You see indeed the defective oxygen on the surface. You do the Raman. It's nearly close to the anatas, but defective anatas. Okay? And colleagues, you'll gather the most important figure is this one. This is the one, colleagues. As you can see, at high temperature is the rutile and anatas, but at the defective ones, their reflectance, the diffuse reflectance, is nearly zero. That means this black TiO2 photoactive in the infrared and can be photocatalytic active. Well, the experiment that you have to do is to contaminate your water and say, here, I have my water, I will contaminate it with methylene blue. Why? Because methylene blue is the dye by excellence. If you decompose methylene blue, you are able to decompose any pesticides that the agri sector is using. Okay, or the large amount of pharmaceutical contaminants that are in our wastewater. And colleagues, what happens here is that you expose, you put your titanium, you ultrasonicate, and you coat, colleagues, with you coat this with the aluminum foil for 1 hour. For 30 minutes. 30 minutes without any irradiation, and you can see that the methylene blue is decomposed. When you wait for 2 hours, the methylene blue is nearly totally decomposed. As you can see, this one is this, the blue one here, and that one is this. So nearly the methylene blue has been nearly decomposed 5%. And colleagues, you may say, how we have coated it with the foil, there was no light coming in, and still it's active. No, pay attention, because the water in which the methylene blue was is at room temperature, 25 degrees Celsius. And that, remember, the is at 25. Therefore, both of them have high emissivity. And the emissivity, colleagues, is Stefan's law, sigma T to power 4. Therefore, huge amount of infrared radiation emitted by the liquid itself, by the host liquid itself, as well as by the tube. And colleagues, that is, how can I say it? And if I tell you how it was synthesized, this big TiO2, you will laugh. You will laugh, but in fact, you should not laugh, because we have used the hibiscus flower, and that hibiscus flower has a compound which is extremely effective in terms of non-linearity, the K3. So, colleagues, that is for SDG 6, and just to share with you this one, how much time I have still, if I have. As you wish, our Commander-in-Chief, please. Feel free, please. That is, all questions are intelligent.
Thanks, Professor Mazhar, for a very nice talk. One very naive question. Your artificial goat milk, which you mentioned for the skin cancer, how you will compare this thing with like conventional sunblocks which people are using after buying from the market? How this
It's one of the most highly downloaded paper and cited paper, both of them, the two. And in effect, we have done it from our case. We have embarked in success just to show. When we embarked in it, our views was to show that indigenous knowledge can be validated scientifically. And we have not embarked in pharmaceuticals. But what is sure is that when you go to, how can I say, Clarivet, you can identify who is downloading that paper. And generally speaking, are pharmaceuticals companies who are downloading it. But we have not done studies comparing it to pharmaceutical product and so on. But it's open access, so everybody can reproduce it. Thank you.
Okay, thank you so much for that presentation. I was just wondering about the INVA. You understand that they apply the end ochre on their skin, and then it is used to reflect back the SS UV. So does it mean that most of the chemicals that we apply on our hand, maybe like Vaseline and the other, does it mean it absorbs? And if it absorbs, so is it the one that contribute to maybe to cancer infection and the bacterial infection? Because maybe you have seen that when they apply that ochre in very high temperature places, it is used to reflect from excess. So does it mean that the chemical that we apply in our body, does it mean that they are absorbed? When then they absorb, they produce a certain heat. It is the one which brings the infection or the bacterial infection. I was just wondering, maybe, yeah.
I must confess, I wish if just can give a direct question. I have not the essence. I do apologize, please.
Okay, so because they apply that infection, they apply that ochre, and then it reflects light. So most of the chemicals that we use, do they absorb all light, or do they reflect some of them?
They are diffusive. They do reflect. Some of them do absorb, but if they absorb, they convert that to heat. So just that UV is converted to heat, to infrared. And the infrared are not, how can I say, dangerous to the skin, to the different layers of the dermis, the epidermis, and so on. What is sure is that all the chemicals which are on the shelf are safe. In this case, it also as more or less to the case of the cancer, we wanted to find out why this community, for example, they do not suffer from the cancer. We wanted to give an is a home for that the Maasai, they do use some products. I think you should really go and find out what type of materials they do use. You will be puzzled to find their effectiveness, and I'm sure that likely you will reach the same type of results than us.
I suggest you can continue.
Thank you. The second case that I would like to share with you is the case of thermochromics are part of what we call chromogenic materials. Chromogenic materials are materials which change color versus light. Being it temperature, being it pressure, been it water. You take the case of cephalopods under sea, they can become completely transparent, the cephalopods, or they become blue, so you cannot distinguish them in water, unless, how can I say, they convert themselves. And also they can take a pigmentation which is equivalent to the coral on which they are sitting. Thermochromics are materials which change color, or their optical properties do change versus temperature. And in fact, one of those who worked extensively on it, on thermochromics here in Kenya, is Professor Kivaizi, originally from Tanzania, but was working here in Kenya, at I think at the University of Jomo Kenyatta University. I would like to share with you this, how can I say, this intelligent material, and see how this photonic can really make a within the sector. I have here 1, 2, 3, 4, 5, 6 air conditioning systems. 6 air conditioning. Colleagues, this material could really make a difference in the air conditioning technology. And these are really a proper and outstanding nanophotonics. In effect, it's a material, this nanophotonics has advanced extensively the ultra-fast laser sciences. Professor late Ahmed Zewail, Nobel Prize from Egypt, he was the first one to demonstrate, to measure the phase transition in time and in space. And I will share that with you, colleagues. Yeah, colleagues, by currently we have 1.6 billion air conditioning units worldwide. By 2050, it is expected that we will be having 5.6 billion units of air conditioning. And this without considering an increase of temperature due to climate change. No, that was a prediction quite a long time. Colleagues, to operate this 5.6 air conditioning in 2050, you need to use the that is by Europe and Japan. You understand this is a madness. C'est pas possible. It's impossible. It's impossible to use only this energy used currently by the USA, Europe, and Japan just to operate the air conditioning. Nonsense. So we need to come with photonics technology that could save humanity at certain extent. And therefore, you need to have smart windows. Windows in your car or in your building would stop the heat to come in when it's hot, and it will allow the heat to come in when it's cold. For such a colleague, why I was pointing housing and cars, because they are the two major sectors who do use extensive amount of air conditioning. And for such a colleagues, here as you can see, it's a thermograph of a house and a car. You see that the heat exchanged, lost to gained, is mainly through the windows. And therefore, in any building, each of the windows here must be coated with an intelligent material. This intelligent is nanophotonic based. It's a coating, like we have in our glasses and so on. It's a coating. So we need to go that route, and for such, as I mentioned, each window coated has to reflect when it's hot and has to allow heat to go in when it's cold. And this material should operate with zero energy input. You should use an energy grid at all. No, this material must be intelligent. The nanophotonic or coating must be intelligent. It has to sense heat. When it's hot, it becomes metallic, reflective. When it's cold, it becomes a semiconductor and allow the heat to come in. And it happened that, colleague, that material does exist. And these are the two reactive. And in particular, Jean Bosco Kanakana, who spent some time at ICTP, was our previous PhD, who is the managing director of Intel in Arizona. Intel is the major producer of the microprocessors. If you have a cell phone or a laptop or any electronic device, it has a microprocessor. And Jean Bosco Kanakana, originally from Cameroon, went to ICTP to be trained effectively, and moved back to Africa, to South Africa, and went to Arizona to become managing director. And colleagues, he was among the first one who worked on this material extensively. And just before starting and the business colleagues, I wanted just to share with you. Here is a toy house. Is a toy house with a window without coating of this material. And the second one, it coated with this material. And both of the two rooms here, the toy rooms, do have a thermometer. Colleagues, they are, how can I say, lightened by a lamp, halogen lamp, which is equivalent of 1.5 sun at this distance. As you can see, colleagues, the temperature that you are reading is 42 degrees Celsius approximately, 41.8 degrees Celsius, while here it's 32.8 degrees Celsius. Nearly 10 degrees of difference, colleagues. 10 degrees of difference. When you speak about heat management, this is massive. It's enormous. It's huge. It's colossal. Do the heat transfer and heat management, colleagues. It's a huge. And knowing that this material does not need any energy to activate it. No, it's intelligent. It's smart. It senses heat. When it's hot, it's blocking infrared. When it's cold, it's transparent infrared. And well, of course, these properties are optically driven, you would understand. And material of VO2 does biomimic the oryx. The oryx is, how can I say, originally it was in Kenya and Tanzania, but a lot in Kenya. For a reason, it has nearly disappeared from Kenya. And among the last ones in Kenya were bought by Qataris, and the oryx in Qatar originated from Kenya. But you have a lot of them in the southern, and hopefully you join us, God willing, inshallah, in Namibia. You will see them. We will take you to the place where you will see the oryx. This oryx is a standing animal. He or she is capable not to drink water for days, for weeks, for months, for a year. How it comes? This animal is capable to do it because, colleagues, it controls the oxygen that is, is consuming. At low temperature during the night, it consumes a high amount of oxygen. And during the day, it consumes less. And the temperature here is around 56 degrees Celsius, colleagues. So, and it does it like this, reversible, day and night, day and night. And the idea is that what can we find a material which has this behavior? In oxygen consumption, we are looking for the electrical resistance. Is there a material which has a high resistance at low temperature and low resistance at high temperature and can have this kind of hysteresis? Well, colleagues, in effect, this photonic material does exist. It's vanadium dioxide. Okay, it's a vanadium dioxide. In a form of crystal, it gives you this change of the resistance, 10 order of magnitude somehow, from a semiconductor to a metal, and on a pulsed laser deposited highly crystalline thin films, it gives you that. And when you do it with the soft chemistry type, you make this nanophotonic by soft chemistry, it gives you that kind of stuff. This more or less just give you an idea about the Hemsbock somehow. But the ideal is this one or this one. Very fast phase. And the time that femtosecond or ultra fast laser spectroscopy was applied to science, it was the which was measured indeed by David Baum and Ahmed Ryle. Colleagues, more or less, this is more or less just summarizing some of the major publications in this field related to it. And colleagues, it's not the unique one, it's not VO2. It's not only the VO2, which is the unique oxide which has this property. Quite a number of oxides do have these properties. But the most interesting one is the VO2 here, because its phase transition is close to room temperature, is 68 degrees Celsius. So from, how can I say, from a technological application point of view, it is of an interest indeed. But you would certainly guess that this phase transition should be close to room temperature, 25 degrees Celsius, if we want to use it as a smart window. Okay, colleagues, and this material, this VO2, has a phase transition around 68 degrees Celsius. It's reversible. At low temperature, it is a semiconductor, and at high temperature, it is metallic. If it is metallic, it is infrared blocking, you remember? And if it's semiconductor, it's infrared transparent. That is why this material is of an interest from photonic point of view. Okay, this phase transition, colleagues, is crystallographic. It's from monoclinic to tetragonal, rutile, monoclinic low temperature, rutile, tetragonal, rutile higher temperature. And this phase transition, colleagues, this phase transition from semiconductor to metal, it's in the femtosecond regime, 180 femtosecond average, depending on the crystallinity of the film. And colleagues, this is the most important graph in this. In effect, this phase transition this phase transition is that at low temperature, at high temperature metallic, there is no band gap, but at low temperature, the d orbitals do split. The d orbital splits and creating a band gap somehow of around 0.7 electron volt, which is low, which is really very low, colleagues. And it's vice versa, it's reversible, as I mentioned. And in effect, the number of cycling is quite high. And colleagues, what controls this is the dielectric constants, of course, as you can guess, and therefore it's the refractive index. At low temperature, it's the Lorentz component which dominates and drives the semiconductor state, while at high temperature is the Drude compound which drives the metallic state, and vice versa. This becomes negligible while this one becomes high. This one at Drude at the metallic state, and this becomes low and this high in the semiconductor state. And indeed, we can come and calculate, derive the dielectric constants and define that and so on. But the most important, colleagues, is this one, is the refractive index. As you can see, colleagues, one of the ideal techniques to synthesize these coatings are laser ablation. Why laser ablation, colleagues? Why? Because during the laser ablation, when you send the parts of interacting with the target, the temperature rises extremely very fast and very fast. You have and so on, and there is a transfer of the material. Therefore, whatever you have in the target, you will have it, which is not the case in a number of thin film deposition system processes. Thank you. Excellent. It's okay. I think, as I mentioned, the most important advantage of laser ablation is that you have transfer of matter. So therefore, the stoichiometry is extremely important because you have to get exactly the VO2, because the vanadium has a valency of 5, so you can generate a huge amount of oxides. And the active one is the one which allows that easily, somehow. Okay. Okay, here, colleagues, we have the refractive index versus the wavelength in the visible and in the near infrared, colleagues, at different temperatures. As you can see, colleagues, these are low temperatures. These are high temperatures. I would like just to single out, you can see clearly, colleagues, the refractive index changes quite significantly in the infrared region. And at 1,000 nanometer approximately, the refractive index moves from 3.2 to nearly half, 1.6. And colleagues, if you take the Bible, the refractive index, the dielectric constant of materials, you hardly, if impossible, to find a material for which the refractive index changes twice like this. It's impossible. If you know some, please inform me. Thank you. And how can I say, colleagues, what happens is that at low temperature, if you make a thin film on a glass, like a smart window, small one, and you measure the optical transmission. At low temperature, the transmission, as you can see, colleagues, the transmission is mainly changing in the infrared, near infrared region. At low temperature, the transmission quite high, while at high temperature is low, it's blocking, and it's reversible. And this is what it gives the potential of this material as this smart or intelligent material ability as a for smart in the future. In fact, Chrysler in Germany does, and BMW do have such a luxury type windows for some luxury cars. Colleagues, this is a photo taken in Singapore. You would see, colleagues, that in each flat has an air conditioning, and each flat has windows. So therefore, instead to use these air conditioning systems, the standard one, we need to coat these smart windows. And these smart windows do not consume energy, colleagues. So there is no CO2 footprint. While the air conditioning, it consumes energy coming from the grid. And that energy from grid comes certainly some CO2 generated technology. And colleagues, not limited to smart windows. You would understand that if the electric constant changes quite a lot, the emissivity of this material does change extensively. And as you can see, colleagues, as you can see, the emissivity is also reversible, and it changes quite a lot, colleagues. Here, the value from that value to that value. And this is extremely important when it comes to cooling small satellites. And colleagues, you would know that in effect the CubeSats are a new generation of satellites. Tesla uses this. The CubeSats are satellites of a small cube of 10 over 10 over 10 centimeters. They are very small. So you cannot use an air conditioning system louvers as in the big ones. You can't. Well, the weight of such a CubeSat is around 1 or 1.5 kilograms maximum. So you cannot use a louver of 10 kilograms to cool down this satellite. No. And now we get that this satellite, as any other satellite, spends half of its time facing the sun, and the other half in the dark, in the cold part. And you have to, in both cases here and there, you have electronics in the nano satellite from overheating, and therefore to ensure that it will operate, it will work correctly. So therefore, instead to use the louvers and so on, classical louvers, it's wise to use these VO2 nano coatings. And that's exactly what JAXA, the European Space Agency, and Tesla are implementing for such a cooling of their small satellites. And this was, colleagues, published by Nagla Norman, a postdoc. She was a PhD and postdoc. And colleagues, in that regard, for tomorrow, if or any time this week, if I am given the possibility, I'd like to share with you how a concept from James Clerk Maxwell, who proposed the idea of nanofluids. He has proposed this in 1867. It was not possible to realize it. It's only from the 1990s, the Department of Energy in the USA and DARPA in the USA embarked in reviving this idea. I would like to share with you, how can I say, how laser action can be extremely very effective in producing these nanofluids. I really encourage the National Institute of Optics here in Kenya to embark in this kind of fluids which have far high enhanced thermal conductivity. So if I have time for such, I will share that with you. And I would like really to finish with this quote, colleagues. This is from late Jomo Kenyatta, who said that our children may learn about the heroes of the past, but our task is to make ourselves architects of the future. That's a really very nice quote, and we have to take it forever and to keep it in our minds. And with that, I wish to express our gratitude. All the results that I have showed you and the 17 publications in Nature, colleagues, are due to these agencies who believed in us in 2005. It was in 2005 that we have launched the Nanoscience African Network, and since then, in 2013, the UNESCO invited us to apply and to host the South. China applied, Mexico applied, Brazil applied, but it was bestowed to Africa. It's in South Africa, fine, but it's Africa as a whole, and I thank you.
Thank you for your very informative conference, and now is the time for questions.
Thanks, Professor Mal, for a very nice talk, and particularly this last smart windows. I have a couple of questions. If we compare these smart windows with VO2 windows, so first thing is in terms of cost, availability, and preparation of such material, if we compare with the glass, what's your comments on that?
Well, how can I say? The cost-wise, it is definitely, instead to go, the cost would be heavy if you use laser-based techniques. But if you use the sputtering standard to make coatings, that's one. That is really what is hindering the cost. In terms of availability of vanadium, China, Brazil, Russia, and South Africa are the major producers of vanadium and its derivatives. In quantity, it is certainly far competitive to the we find use silver, for example, which is semi-reflecting. But soon it will come. In particular, China has embarked in a strategic program on smart windows. So when China goes that route, that means it is indeed they will come. They will definitely come with a large production.
Another question, sorry for that. This is more like thermotunability with the heat, it switches, it's like from metal to semiconductor. Do you know any material which can be tuned, switched using electrically tunable material which can show this kind of delta? And
yes. Tungsten oxide, for example, which is called the blue bronze, is, can I say, such a kind of material whereby you have tungsten oxide thin film how can I say, and another glass coated with nickel oxide, and in between you inject lithium electrolyte. Why? When the lithium diffuses the tungsten oxide, it will create a polaric configuration, and therefore the tungsten oxide becomes blue. Really can be blue dark, and related back to the electrolyte, and therefore the tungsten becomes transparent again, and the system becomes transparent. Definitely there is. And the other materials who do also such a kind of variation of the optical transmission are the viologens. They are UV activated. When there is quite a lot of UV, they become dark. When there is less UV, they become transparent. But the viologens are extremely expensive, and they are not biodegradable, one, and second, the life cycling is minute. In the chromogenic one, in the electrochromic ones that we call electrochromic, the tungsten ones, the system is not a single layer. Here, it's a multi-layered system, and you have problems of sealing and so on. And also the electrolyte is not UV stable with time. So it's the cycling is also a parameter when it comes to this. But as the case that we have showed here is enough for the Middle East. It does work perfectly in the East.
Hello, my name is Dan Chingama. Thinking around that, is it possible maybe instead of dissipating the heat, can it maybe the surface combined with a solar cell? Also the sun is also converted into energy which can be stored in batteries.
More or less your question. Can you go straight forward to the question?
So I was asking, so is it possible for the surface also to be combined with a solar cell, or will it bring some issues?
Remember here, it is for how can I say, Gratzel was thinking cells, was thinking about combining such a material, collect the heat. And why? Because a disolar cell or any system, in particular for the photovoltaics, an increase of 5 degrees Celsius of PV will cause a loss of 1% of its efficiency. So, and the one which is heating is the infrared, and Michael Gratzel was thinking about using such a kind of VO2 to reflect the heat and to ensure that the system is cooled somehow. Yes, correct. He thought about it, and you know that he is the commander-in-chief when it comes to solar cells and the perovskites. Please.
If there are not more questions, let's give thanks again the speakers for the very nice presentation.
Use it to be a motorbiker. I have had a crash. Yes, please.
Thank you so much, Humberto. Thank you so much, very kind. Oh, sorry. Sorry.
So our next speaker will be Habato. He just proceed with what he was to discuss yesterday, and discuss about the photothermal spectroscopy. So welcome and proceed with your presentation.
Okay, good afternoon. I will conclude what I started yesterday about photothermal spectroscopy with lasers, but today I will speak a little about LEDs. Why LEDs? Of course, following the very nice conference of Dr. Malimasa, I have to speak also about low cost. LEDs, because LEDs are very expensive, they are very stable, they are very compact, and we can have whole visible, even infrared spectrum. Therefore, the size of your device can be reduced. We can have less bulky device. Because of that, we are proposing this technology with LED. This is our proposal, similar to what we had yesterday. We have the probe laser collimated. Remember always, and I will explain why, the collimation of the probe laser gives a lot of, we will see this, collimated by two staring mirror here, and we send the light through the sample here, the sample, okay? And then this light is reflected by a condenser of a microscope with high pressure. This condenser reflects the light back and path because the sample is located very, very near to this condenser because the working distance is very, very small. Therefore, the light passes twice and is reflected by this set of rise detector. I will explain why. How it is possible to use LED, green LED, in this case 520. We bought around 5 LED with only 50 euros. And I am using this month continuously, chopped, electronic and modulated, and still is going. This LED, of course, the mission of the LED, you know, is incoherent. We spoke here about the incoherent sources. You know, the K vector is oriented in all the directions. And this is very difficult with the LED to reach the diffraction limit, it's very difficult to focus in less than 1 millimeter. Nobody was able to do photo spectroscopy with LED. This is the sign. The LED diverged, and with this lens, we were able to focus in a radius of around 4 micrometers, less than a meter. And at the same time, modulated by this signal generator at different frequencies. We use 1 Hz, 6 Hz, and 11 Hz. The results are the same. I will present only the results at 1 Hz. The same condenser acts as a mirror. It reflects back the light. The probe being passed twice through the sample. Then we are using another problem with the LED. The light and the Rayleigh distance is very short. You have to use very short cells, path length, 1 millimeter. In this case, we use 2 millimeters because you are not exciting. This, the path length, instead of having 2 millimeters, a 4 millimeter path length cell. Then the signal will increase twice. We expect this. However, also we implemented another method here. That when the probe beam is estimated, I will demonstrate this using the theory of thermal lengths and also the theory of Gaussian beam propagation with a at certain distance. In this case, 220 centimeters exactly. It depends on the radius of the excitation beam onto the sample. The maximum size. And that we have this system in order to make the very compact. This a different position allow us to optimize this. Can you? This is the vision intensity. You can see it's not as a laser, but it's good. It's around 30 nanometer bandwidth. It's not or gas, but I am working with liquid. It's perfect. The liquid, they have very broad bands and very stable also. This is the thermal length signal, like the similar procedure I explained yesterday. We have the thermal length signal coming from this sample. We use safranin O in water at this concentration, micromolar, 6.2 micromolar, and why we use safranin O? Because it's a fluorescent dye, very used in biochemistry. And we wanted to develop, because this device, if you can see here that I to tell you, we also can measure the fluorescent. Can you come back? Here, this is an optical fiber. System to simultaneously measure the photothermal signal and the fluorescent. This is why, as a model of concept, we use a safranin at different concentration. Therefore, we form. This is the distance from the detector to the sample. We change the detector position, and we measure the thermal length signal. You saw before the thermal length signal in the oscilloscope, and you can see how the signal increase exponential. Around 210 centimeters, we have the maximum signal. This is experimental value, and the red is the fitting curve with the theory that you saw yesterday here. As you see, there is very good agreement. But this is not only explained by the theoretical model. With the simple Gaussian equation, you will understand why the signal increase. Why nobody knew about this before. These are, of course, the parameters that we use. Very simple. Only two. You have, okay, this is the divergence angle of any Gaussian beam. Remember, we have a Gaussian helium laser that is perfect Gaussian beam, 10, 0, 0. The divergence angle can be approximated by lambda over pi, and this is the radius of the probe beam onto the sample. However, our probe beam is perfectly collimated, expanded and collimated. Then, this radius is constant and very large, 3 millimeters. It means the divergence a lot. It's very small, almost no divergence. When you have a collimated probe beam, you can see the same spot there, the same spot around 1 kilometer. And this is the important fact. Therefore, we substitute this in thermal lengths. The thermal length signal, as you remember yesterday, is defined as intensity with thermal lengths, the minus thermal length, intensity, radius. This is another definition. The radius of the beam, because with thermal lengths, the radius is proportional. And this theta is proportional to the phase of the we can substitute here. And then you can see here that this difference in divergence makes important and contribute thermal length signal. And now, if you have a collimated beam that is constant and perturbed without excitation, okay? When we hit the sample and we have excitation, when you hit the sample, you create. If you consider the radius of this micro length coming from this micro length is the same size of the excitation beam, because you create this micro length with the excitation beam, with the LED that is around 1 millimeter. It means this radius is very small. If the radius is small, as you know, the divergence increase with the distance. As you propagate in the space, this divergence increase. The thermal length is defined as the difference between the beam, the beam intensity with thermal length minus the beam intensity when we don't have thermal length. Then this increase, this divergence created by the thermal length and the difference with a collimated probe beam at this very low divergence. And this is the reason why this amplification of the signal increases twice, as you can see here. Then we have a little saturation. Of course, this saturation is because of the effect of the pinhole and the size of the excitation beam. If the pinhole too much, then the intensity will start not sensitive enough to change. And we increase the signal 4 times using the multipass. We use also in the past 10 pass. In this case, with 2 pass was enough to use a LED of 18 milliwatt power. We did a lot of measurement. However, I want to stop here because this work is on the review now. I don't want to go ahead more. But we did also fluorescent measurement. We did Raman, and all the measurements were in perfect agreement. And with this, I want to conclude here. If there are questions, I will answer the question. In the meantime, Jared will change to the next presentation related to digital holographic microscopy. Okay, if there are not questions, it means it was clear. I will go to digital holographic microscopy. In digital holographic microscopy, we had, during last week, a lot of lecture here. All the speakers, Professor Pereira, Alessia, they spoke about interferometry. Professor Pereira derived the integral, propagation integral that developed the concept Fourier transform and Fourier inverse transform. Then I will use the same concept, of course, but I to the application, the configuration of the device. Also, Alessia spoke today about common path interferometry. I will focus on also common path interferometry, and I will describe this ISMA microscope that is based on common path interferometry. I will go very fast through Mach-Zehnder, that is the basic setup for interferometry and for digital holographic microscopy. I will come to our setup. I will describe completely this, and you will understand why there are advantages. First of all, also, last week, also about the general holography. We know about that we need two beams. The object beam, okay, this is of reflection mode. We have the object beam collected by this lens, and we use this as a reference beam and on a photography screen in the past, but nowadays people are using CCD camera. Because of that, they call this also digital holography. You know, and there are two basics, basic configuration, similar to what I showed before. You have the object, you have the object beam, and you, with the beam splitter, you take the same reference beam using the same laser, and then you have, this is the common interference pattern that we see. If we have a photographic plate, we have to illuminate with a coherent light this photo in order to see the virtual image or the hologram as you can see here. Okay? Process. Use a propagation. It's the same equation that Professor Pereira showed you yesterday. Or last. But what is important here to understand the steps, the block diagram that we have to follow in order to process after, because it's very easy to have this hologram from this device in the CCD camera, but we have to follow some that we describe. We record the object and the reference digital hologram, as we saw in the previous slides. Then we have to do fast Fourier transform. I will show also this. And the frequency selection, select and center the frequency. There is a numerical propagation. Then we propagate the Fourier spectrum, okay? And we do the complex amplitude Fourier space. And then fast Fourier transformation. And then we get the phase and the amplitude, as we will see here. The phase and the amplitude. And from the phase, we can get the refractive index distribution, the thickness distribution, and so on and so forth, as you can see here. This is the normal procedure that use in digital holography and in holography from the that is the most important method that we can get. Remember that in holography we work with the phase of the beams. We work with the amplitude. That we are able to analyze even transparent samples, because what we look is that the refractive index different. And refractive index different means different phase. Okay? As you can see here, and you can here, the holograms are numerically reconstructed using the angular spectrum propagation. This is the question that we did last week. I will show you now again. Of course, in a code, in MATLAB, if you want to see this, you can go to this. We have the code. You will see this that I will show you right in there, and how is the process. The same process I approach in which the intensity and phase information of the object could be at the by propagating the angular spectrum of the filter from the Fourier transform of the complex amplitude. Okay, this is the scheme. General representation of this is off-axis. I will speak about on-axis or common path. In this, we have reference beam. The phase is what matters here, the phase of the reference beam and the phase of the object beam. The object beam is taking difference in the phase, and it's this information in this interference pattern, as you can see here, this in the fringes pattern, because the different phase of this object or particle that we are analyzing there. Then it's the same. If we have digitally, this is or digital, the same. And this is what we were expecting before, the angular propagation, the Fourier transform, and the inverse Fourier transform for the analysis and the processing. After that, I have to start with the most simple setup, Mach Zehnder. Mach Zehnder is a very well-known, this is a Mach Zehnder digital two microscope objective to make the two beams, the curvature of two beams similar, okay? The object and the reference beam at the camera position. Then register here the interference pattern we saw there. Mach Zehnder configuration, of course. I am speaking now about transmission mode for transparent objects. Okay? Then, the detector is at the image plane of the magnifying lens, if we have, and provides both amplitude and thickness information from the single hologram, single shot. This is single shot. You will see here that here two shots. I will. And we can use it for real-time cell morphology. The holograms, the interference pattern, are optically recorded, as you can reconstruct light diffraction from the interference using the diffraction integral that Professor Pereira explained and I showed you in the previous slide. This is, for example, for red blood cell, one example. You have here the parameter of the microscope objective used. Blood cell is a very good example because you know they have a donut shape. I will show also another example that we took with this microscope. Okay, what is the problem with Mach-Zehnder? In Mach-Zehnder interferometry, the temporal stability is not good. Why? Because we have vibration. And if you have vibration, you need to have this on the vibration, the acoustic of the sound, change the reflecting of the medium and introduce noise. Then you can have a noise interferogram. You can remove point. This is why another example in digital holography, see here the typical hologram, this using two beams of axis also configuration, and also from this the phase different. We have to consider, you can come to ISMA and ask her how to process. You will see that in one step of this, after we solve the Fourier transform and the inverse Fourier transform, and we get the phase distribution, then have also digital holography. I'm speaking about cells for us are transparent. We use transparent material, but I have to tell you that there is also digital holography microscopy for opaque sample. Of course, you have to say, because if you want to analyze the surface of this sample, you need to get the reflectance of this sample, like in this case, and to say another reference beam to be both combined onto the sample and to have the interference pattern. This is for opaque samples. But now I want to concentrate, after we have this background, on common pass digital holography using Fresnel B-prism. This is what we have here in this setup, described also here. Which are the advantages of this setup? First of all, no any vibration affect the high temperature of this interference pattern. Second, it's very compact. We can common microscope, low-cost microscope. For example, we remove the lower part. Here is inverted, okay? It's inverted here. You know, microscope, you have the illumination source, the white light source coming from here. The sample will be here, the microscope objective here, and we have a binocular or CCD camera. We remove the upper part. I will show separately. We remove the upper part and the lower part. By the way, I use the condenser of the sample for this, for the focusing of the LED, the same condenser. You can third advantage, a diode laser. You don't need coherence. Even you can use LED. Why? Because it's common path. The beam is in the same path. Then you don't need helium neon laser to have high coherence. And you have here the Fresnel biprism and the camera. All this distance matters. And this distance. Okay. The microscope objective, the sample, we have a condenser, and part is divided and interference onto the CCD or CMOS camera. And B is this distance, is the distance between the Fresnel biprism and the camera. Okay? Then we can control this distance, and this is another advantage. You can control the density depending on your sample and the resolution that you want to have. Okay? Then you have this angle here. Okay? What angle? Very important. You cannot use any Fresnel biprism. The Fresnel biprism has to be polished at this specific angle, because as you see here, this angle also matters for the density of fringe. Okay? This is the scheme, the sketch of this setup. I will explain also in detail here. We have, okay, this is the microscope body. You can see here, this was 3D printed. This part, upper part, printed also. The same microscope, okay? You have the CMOS camera. The Fresnel biprism is here. You can see. This is the holder of the prism, also made using 3D printing. The sample, we can regulate the diode laser. The laser we use very cheap. 3 volts. The diode laser here. The same here. See that this is a common microscope, optical microscope, and we use the same microscope objective. The laser and the camera. What will be important, you know, we have here a conference and experimental session in the afternoon about metamaterial, will be to reduce more the size of this prototype using metalanes. This will be very nice. You have high aperture angles, higher aperture angles, and you can reduce the size of the device. Okay. Now I am giving you one. If you want, come to Isma. She will explain you this using the program in MATLAB that we have. We wanna have a code also in Python. We will do working on of the red blood cell. You can see in the instrument in the fringes correspond red blood cell. In B, you have the Fourier spectrum. You can see, this is what I explained in the block diagram. You have the Fourier transform, and you filter the frequency. You filter the frequency here by windowing the first diffraction order. We have 2 diffraction orders, and the central. We have the same information in both +1 and -1. Say any of this, okay? And then the intensity, the phase map of D, okay? And this is the thickness distribution, see in micron here in colors, of red blood cells. Okay? Intensity, and we can get the thickness. We can do also M profile. We can have the profile distribution of this. This also introduced in the code that we have, and we can have this donut profile exactly as the cell you have there. Okay, and finally, I want to speak about the system we developed in this world recently, last year. For the first time, we combine also digital holography with thermal lens. We did also yesterday, I spoke this, was another kind of digital holography. We used yesterday a plate, that is common pass. Now we are using sender interferometry. As you can see here, we have a Mach sender interferometry. This is the probe laser collimated, sent through the sample. Remember, the 2 microscope objective is only to have the same wavefront of your reference and object beams. And we have the sample here. In this case, explain you, we introduce also for the first time microsphere assisted photothermal lens detection integrated with digital holographic microsphere assisted. Publication about this in conventional microscopy and in digital holographic microscopy, but not in thermal lens. This is the first time. As you know, when Alessia was teaching yesterday and in the day about the microscope, you have the numerical aperture of the objective depending on the aperture angle or a segment angle, and that this is related to the resolution of your system. In order to increase this resolution, method in which, for example, that more the light, you add silica bit sample after microscope objective. Okay. Here, this is the microscope objective, and the silica bit is here. The sample. And then you increase the acceptance angle, and you can convert a microscope objective that is 10x, 4 times more, to be 40x, and you increase the resolution using a simple silica bit. And this is what we did, and we combine also with thermal lens. Here, the silica bit, we take the reference beam from here, from this beam splitter, another beam splitter, dichroic mirror, and we recombine here onto a CCD camera. We also measure the thermal lens signal at the same time, as a matter of comparison, because it's simultaneous. What we use a communication laser 532 modulated at different frequency through this dichroic mirror that allow the transmittance of 532 and 100% the red beam. There's a problem with the microscope, with the, and then what we did is to use as a proof of concept different sample, 40 micron silica bit in a fluid, in a microchannel. We flow different silica on this microchannel inside ethanol, and then we process, okay, the same procedure we explained before. We took video in this case, and we, in this case, we are showing two particles that are visible by digital holographic microscopy. But at the same time, we took the signal from this particle. When the particle passes through the laser light, give a thermal lens signal, a peak. How we know that, and that we know that the signal is coming from the particles? Because we flow ethanol without particle, and we have this thermal lens signal, constant. no signal. Then, from where is coming this signal? From the focusing of the particle and the absorption of ethanol. Then we are detecting the presence of the because of the particle. Then we can count and we can do deep profiling. This is what we propose with this work. Because this particle here is not very clear. This particle goes deeper in the channel, goes up. And because of that, the thermal length signal is different because they have different focusing on the of view. After that, we did the same with red blood cells. With red blood cells, okay, we realized and we saw and read some paper in which they reported the focusing capability of the red blood cell. They are donut shape. They are able to focus also the red and the green light in general. And we tried with red blood cells. Actually, in this case, we are showing the two red blood cells at different depth in the channel. And you can see also here, you can see shape of this using digital holographic microscopy after processing. See the position here. We did in profile, I mentioned before. You can see here the of these red blood cells, and also signal. You can see when blood cell, no signal. That we speculate that is coming from the liquid. It's coming from because of the focusing capability. We embedded these silica bits on a polyestyrene. It's a polymer, very thin layer, micrometer, thin, transparent. We embedded many particles there. And we did a scan. We have a mechanical scan with very high precision. And we scan it. You can see here the scanning. This is the RAS of this scanning. Okay? And this is the thermal length signal and the digital holographic or thickness profile of the particle, 40 micron. Okay? You can see here one peak because we scan it in one direction and poof, peak. Then coming back and we pass many times through the same sample in order to construct. Using thermal lengths also we can reconstruct this image, but we wanted to only the peak. You can see there is no signal outside the particle. And also we suppose that we increase the focusing capability, as I demonstrate also in ethanol, because all these samples absorb very well the green light that we were using as a excitation source. We propose this as a proof of concept, but we want to demonstrate also, okay, we are proposing deep profiling, measurement, and detection, but you have to demonstrate at least one measurement. We measure the thermal diffusivity, we fix one particle, and we measure the thermal diffusivity of this particle that was report to also yesterday. But the first work, the idea was to demonstrate the concept. And with this, I want to go to conclusions. I will speak first about digital common pass digital holography using Fresnel B-Prism. The stop is very compact, cost-effective, and easy to implement. It could be applied to many conventional optical microscopes, as you saw here, which use a low-cost diode laser, €3. Simple by adding every prism and to align. The advantage of the proposed technique is Sub-nanometer, we demonstrate this in a paper. Sub-nanometer temporal stability that is measured and is around 0.11 nanometer. It's better than Mach Sender. And without any vibration isolation, like this. In any table, you can take also here and measure. Precise adjustment of the intensity ratio between the object and reference beam, because they are the same. Even without accurate alignment of the beam prism, leads to the high contrast of fringes. Without alignment, you will see also fringes. Of course, if you have perfect alignment, you will have the perfect contrast. But without any alignment put there, you have fringes and you have the image. You need, I have to speak also about the disadvantage, okay? After advantage. The period of fringes depends on the axial position of the prism. As you saw, remember the equation? Frequency adjustment can be easily performed, which assists in studying the micro objects with different size and shape. The comparison between the presented technique and the conventional Mach Sender interferometer reveals that our proposal has higher temporal stability. Furthermore, we integrate this. Okay, this is the second word. I have to tell also the disadvantage. Disadvantage is that if you add a cell at the center of the objective, you have twins image. You have to take one shot with the cell and then move without moving the focus. And in the microscope slide, take a second image as a reference beam, and then you process. Even if you add the cell at the middle of the field of view, and you have this precision, with a very precise system, you need only single shot. But if you have many particles that we have, you will have twins image. But this can be also removed after processing. It's not a big issue. But I have to mention also this, okay? We integrate digital holographic microscope with thermal lens detection. This is the last topic I presented to you. Also, we demonstrate the concept of, for the first time, microsphere-assisted thermal lens spectroscopy that can enhance the photothermal lens effect and to see transparent objects, okay? We presented the proof of concept, experimental, on a fluid, solid, and biological sample in the 3 common use media. And the induced TL effect due to the microsphere assisted was strong. We suggest the microsphere assisted TL digital holographic platform to be a high sensitivity, counting, and depth profiling approach based on the TL effect. Of course, the measurement of the thermal diffusivity of the particle. This is one of the proposal in this last point. And to conclude, thank you very much for your attention. I am ready to answer questions if there are. I saw Alessia writing a lot there. Then she has a lot of questions for me. If I cannot answer, I will send you to the papers.
So thank you very much for this presentation. Now we allow Alessia to be the first person.
Thank you very much. It was interesting. I didn't have the time to show the common path interferometer that we also use. It's different.
To introduce it.
I wanted to. It would have been cool
very
if
nice.
I had introduced it properly. But anyway, this is interesting parts. So it's a very. That's why it's also so stable.
Only the sample position to focus, but I have to tell you that we have numerical focusing. The sample need to be in the focus because in holography, you know, you have all the planes can be reconstructed.
Okay, I have 2 questions. understand is the price. How much does the B prism cost?
See,
Is that expensive?
the B prism, if you order, if you buy into labs, I didn't buy into lab, it costs around 300. This prism doesn't have the angle.
Exactly.
This of this word also, specific angle that you need this interfering pattern. Then you will pay, but you don't have. You can have a B prism. I got very cheap because I bought around. I am collaborating with a Pakistan group. I also supply them, and other groups was around 75 euro because they reduced me the price. We took together, 2 persons, 5 for me, 5 for the other, my collaborator, and this was the price. Because of that. And they did this in Iran. They polished and they did for me, and it's perfect, very precision.
Okay. Yeah, because for example, in our case, our crystals, they are expensive.
See, in this
so
case,
this one is not.
Yes.
Okay, I see. I had another.
The camera was also very, very cheap. I bought the camera for 200, but you can use even a webcam. Of course, the quality is not the same, but you will have results.
That was my other question. So on the camera, the peak.
No, because we are taking, if you are taking an image of a static sample, you don't need high speed. You only need to take 2 shots, and that's it. This, for example, this microscope, I don't know if it's around, they are using a webcam, a camera, or a little better than. But you don't.
Because very often, like cameras for the mobile phones, the pixels are very small. So, for example, in light field microscopy, you want to have pixels, for example. So I was wondering.
3.5 here. Use in the camera I have in this.
Okay.
3.5 micrometer. I bought this in Alibaba, but this Basler. It's the same Basler. It's a very good camera, and it can reach even 900 frames per second. Okay.
Oh, no, it's great. I mean, yes. I guess, okay, also because you don't need very high sensitivity. No, okay, I think it's very, very nice.
But, Jared, we forget the important. The result is
yes,
after your.
Yes. No, the only other question I had was on in the reconstruction. So you have to apply the retrieval for the phase and the amplitude?
The angular spectrum of propagation.
Yes.
So there,
yes.
We apply Fourier transform, then you select the first order, you filter, because you select frequency there, you select, or high frequency, you select as much as possible, and then you apply the reference and the Fourier inverse transformation. And you get the phase distribution, the thickness distribution, the intensity distribution, and so on and so forth.
And that's quick.
Yes, very quick, in a few seconds.
Great,
yes.
Thank you very much.
Let's see the application of this microscope. Some of them developed by my student. It's only to show the capability of this setup. Harry will show this video. The same setup, you will see the applications in red blood cell, cancer cells, for visualizing, detecting. You can see here movement of fibroblast cells. See the first orders. We select. This is filtering. Fourier spectrum. The process of water evaporation as a matter of demonstration. You can see the water. Red blood cells membrane. This is because of the highest temporal stability. You can test red. We didn't this. It was another group, but I am using as a hair cells contraction. Also, we didn't this. Don't ask me more, but it is possible using the same microscope. No, not mine, but the same. Human bone cell division. You can show cell division also. Movement of cancer cells This was done of my student, of my collaborator that also built this with me. Phase distribution of or division. And finally entering the fluid in microchannel. Follow the process. In this case, you need to take a video and process. No, it's a little more complete and more time. It's not only single shot. You can see the fluid reaching the channel, and that's it. More questions?
Any other question?
Thank you. Umberto, please. The photos that, the images that you were sharing with us.
Yes, exactly. Not all. Presentation, yes. But this video, there are not all maybe one of two. The others are available from other groups, and I use. Yes.
Thank you very much. Question from our other participants. So a quick one. Why use MATLAB or you have or you are?
No, with MATLAB, imagine this setup, the cost of this setup, if you calculate the French epiprism at the camera, the rest, you took all microscope, and you less than 400 euros, let's say, maximum. And if you have a MATLAB program, you have to pay 20,000 for the course. We have the ICTP license, and you can use it. But the idea with our student, Isma and Aquila, have this student from Quasin working with me now, and they are developing the Python free software, because no sense to have a device that costs less than 500 and to pay for a license in MATLAB for 20,000. Because MATLAB is easy code, you can develop, but you can translate. You can translate this to another program. Free cost program, free software.
Is the reconstruction of the orogram image affected by the laser type?